Good morning, everyone. So we are ready with our day 4 session. Shipra ma'am, over to you.
I feel privileged. Hello, can you hear me?
Shipra, you are audible.
Okay, thank you, ma'am. On behalf of University School of Basic and Applied Sciences, Guru Gobind Singh Indraprastha University, I feel privileged to welcome you all to the last and final technical session 3, day 3 of the International Symposium on Synthesis and Characterization of Smart Materials and their Potential Applications. The distinguished speakers for the day are Professor Michelle L.F. Lerch, Head, School of Physics, Faculty of Engineering and Information Sciences, University of Wollongong, Australia. Professor Atul Khanna, Department of Physics, Guru Nanak Dev University, Amritsar. Professor P.D. Sahare, Department of Physics and Astrophysics, University of Delhi. And finally, Dr. Meng-Lin Tsai, Department of Material Sciences and Engineering. It's an honor and pleasure to have you all with us. On behalf of USBAS, I thank you for accepting our invitation and sparing your precious time for giving these invited talks. We look forward to hearing you. Today's session chairperson is Professor Venugopalan. Professor Venugopalan is Professor of Physics in University School of Basic and Applied Sciences, Guru Gobind Singh Indraprastha University. She completed her PhD from School of Physical Sciences, Jawaharlal Nehru University, New Delhi. She was subsequently a postdoctoral fellow at the Tata Institute of Fundamental Research, Mumbai, and the Physical Research Laboratory, Ahmedabad. Her research interests and work are in the field of theoretical areas of foundation of quantum mechanics, quantum classical connection, emergence of classicality, quantum coherence and decoherence, confined quantum systems, and quantum information. She is very hardworking, dedicated, and organized researcher and academician. It's my pleasure to introduce Professor Venugopalan. I request you, ma'am, to please conduct the session. Professor Anu, please.
Yeah, can you hear me?
Yes, ma'am.
Yes, so good morning, everybody. Good morning, everybody who's logged in from India, and good afternoon to Professor Lerch, and if Professor Tsai from Taiwan, I think it's afternoon there too. So it's a pleasure to be here, and I'm very happy to chair this session. We have 4 talks, 30 minutes each, with about 5 minutes for questions. Like yesterday, let's try to keep time. So I'll ask the speakers to speak for 30 minutes, and then we'll keep 5 minutes for questions. So let me just not waste any more time and introduce the first speaker for the day, which is Professor Michael Lerch from Australia. He's the head, School of Physics at the Faculty of Engineering and Information Sciences at University of Wollongong. And I have a brief biography. Actually, it's not brief, but I'll make it brief to save time. Professor Michael Lerch graduated with a PhD in solid-state physics, and he is a founding member of the Center for Medical Radiation Physics, which is CMRP at the University of Wollongong. He's currently head of the School of Physics there, and the CMRP is research strength of the university, and he's working within a field of research and industry institute, and it's, I believe, ranked as being well above world standards. So we're indeed lucky to have you. Professor Lerch applies his expertise of electronic properties of semiconductors to the design and development of novel solid-state-based sensors and instrumentation for application in radiation medicine. He's also interested in the optimization of radiation medicine created by the physical and semiconducting properties of engineered nanoceramics and semiconductor devices in different radiation field environments like photons and charged particles. He's interested in the real-world implementation and the application of real-time devices designed to operate in vivo from a targeted diagnostic, imaging, and radiotherapy point of view. And there's a lot more. He's published many papers and has several years of undergraduate and postgraduate teaching, and has supervised more than 25 higher degree research students. And his research and development projects have been realized through national and international competitive research funding agencies, and he has secured over 5 million Australian dollars as a chief investigator. So this all sounds very exciting, and he's going to talk to us on smart silicon detectors for application in radiation medicine. So without further ado, I hand you over to Professor Lerch for his talk.
Thank you very much, Professor Venugopalan. It's a very, very kind introduction. I appreciate the invitation from the organisers. I've been in most of the sessions throughout the few days, and I've found them very, very interesting. And looking forward to today's speakers. I think they're an excellent lineup again. And so I'd just like to congratulate all of the local organising committee for putting on such a fantastic event. So I'll start to share my screen. In this case. Okay.
Yes, we can see you.
Can you see that? Good. Excellent.
Yes.
If I lose everything, of course, I'll try and bring things back in terms of the chat and everything like that. Since we do this all the time in lectures and things, we lose everything. So I'm going to be talking about smart silicon detectors for application in radiation medicine. So we'll get straight into it to try and save time. So I'm from the University of Wollongong, of course. I might just walk my pointer over. Laser point. That way we can keep going. So a brief introduction. So my talk outline will include a bit of an introduction and background. And then I couldn't help myself with the other talks that have been going on about nanoparticles and things like this. So I thought I'd better throw in a couple of slides about some of the work we do in this area. Very briefly, it may cause me to go over time, but I'm sure I'll be told to stop when it's time to stop. And then once I do that, I'm going to talk a little bit about some applications of these smart detectors, so silicon detectors, in different radiation field environments. So one's in photon therapy, so conventional megavoltage therapy, as well as brachytherapy, and then talk a little bit about microdosimetry in hadron therapy, and then finally synchrotron X-ray microbeam radiation therapy. So different sensors for different environments, and I'm really trying to demonstrate, so sort of demonstrate going across from detector development right the way through to applications. And so I'm going to focus on the application component. So just in case you're wondering where Wollongong is, basically, we sit down here, about the northern suburbs of Wollongong is about 30 kilometres from the southern suburbs of Sydney, and we're separated by the second oldest national park in the world. And so you can take the coast road here if you want to come down to Wollongong when you come down from Sydney, and we have an annual bike actually which comes down every year. So this is Wollongong, a picture of Wollongong City itself, and the university campus sits just under here, under this Mount Kira we call it, which is about a couple of kilometres from the beach, very close. The School of Physics itself, if I put my School of Physics, the head of School of Physics hat on, if you like, we do lots of research, of course, in many different areas, which are listed here. And we are ranked very highly in Australia. So this is the Excellence in Research Australia. So we're ranked at the highest level possible for our research. And so we have a very active research environment which is engaged in all of these different areas. So my specialisation is moved across from solid state physics, is where I did my PhD, but I've moved into medical radiation physics environment. And so, as I said, I'll talk a little bit about nanoparticles first of all. So this is some of our nanoparticles that we've been developing for applications in theranostics. So that means both in therapeutics and diagnostics. So we're trying to combine the two. to create an environment where we can not only see where the nanoparticles are, but we can also treat with the nanoparticles by either attaching some drug or something like that, or having some high Z component, so we get an interaction there with the radiation environment that we're working in. And so you can see here, this is basically some in vitro experiments. So these are some cells, and these particular cells are very nasty cells. They're brain cancer cells. And so the brain cancer cells are taking up, so this is two different types of nanoparticles produced in two different ways. So T nanostructured particles and P nanostructured particles. And if we zoom in on one of these cancer cells, you can see here the nanoparticles are being gobbled up by the cells in the in vitro, so in the dish, if you like. And then once they do that, then we can expose them to irradiation, and we can look and see how the survival fraction of these cells. So this is on a log scale here, the survival fraction. And so depending on what type of radiation environment, so this is 150 kVp. So this is very low energy X-rays, I suppose, if you like, from a therapeutic perspective. And this is higher energy, so 10 megavolts X-rays from a normal LINAC in the hospital. And we're looking at the survival as a function of the dose that's being delivered here. And so you can see here, if we put no nanoparticles, then it has a certain survival curve. And then if we add some nanoparticles at 50 micrograms per mil here, its concentration, then we get some additional cell death here. And so there's these cell studies. And so it's very, very, very exciting to see this on a log scale, of course. We see some significant improvement here in treating this particular cell line, which is renowned for being very radiation resistant. So it's very difficult to kill this with normal radiation. You need a lot of it in order to be able to treat this cancer. However, you can see here that if we go to higher levels, so higher concentrations at 500 micrograms per mil, you can see we don't get further improvement. And so this is a lot of physics that needs to be understood what's happening here, a lot of chemistry and a lot of biology. And so, again, this is more inspiring work which is going on with nanoparticle research in general. I find it extremely multidisciplinary. And so we have to interact with chemists and biologists and not only physicists to make these whole systems work and to understand these systems. So it's really exciting sort of work at the interface of these disciplines. And so, and there's a lot of work that can be done in these particular areas. And so we see similar results at the megavoltage region. So just quickly here, you can see a similar improvement basically in the treatment. But again, we see this sort of saturation of what's going on. So we need to understand what's happening about that and why that's the case. So we know, and so this is just an illustration of how these cells. So these are the cells here in the in vitro dish. So this is time-lapse photography. And you can see here the nanoparticles sitting inside the cytoplasm of the cell. And basically they're gobbling up these nanoparticles as they accumulate, so in time. And you can see basically this one over here, if you have a look at it over here, and taking this nanoparticle directly into the cytoplasm. Okay, so it's eating up nanoparticles in time and loading themselves up. Okay, so that was just a repeat of that again as well. And so very interesting to see the ways in which the timing, everything is critical. So you need to understand these systems extremely well if you want to apply them in the clinic, basically. That's very, very important. It's not only important to be able to have it work on the nanoparticles working on the cancer cell line, okay, but we need to also make sure it works on the non-cancerous cell line. Okay, so these are non-cancer cells here, and you can see here as a function again, so increasing the concentration. We see the normal cells are actually hit quite hard by the radiation, okay, normally when you've got no nanoparticles compared to our radio-resistant cell line, doesn't get hit very hard at all, so you get lots of survival there. But if we add our nanoparticles, we can see we're getting some selectivity going on here, which is very, very important for nanoparticles. And so when we add our nanoparticles, our normal cell line is not being hit so hard compared to the cancer cell line. And so it's extremely important. We do get some further when we add in more concentration of the nanoparticles, but not much. And so we can see there's a limit there, which is what we saw with the in vivo, with the other in vitro experiments, I should say. And so this is very interesting work in the sense that we can get some selectivity here. We also get some specificity, and we're getting quite a significant improvement in our therapeutic outcome, if you like. And so then we can use this to try and improve our imaging. And so I've just got a little slide on that as well. Okay, because this is what we normally use. So this isn't our nanoparticle, this is using iodine contrast agent. This is a CT scan of an in vivo experiment that we've been doing. And we want to try and improve this contrast, because what we need to do is define our tumour volume, which you can see here, okay? And so we want to be able to do that better, okay? And so that we can then define the target that we want to treat more precisely. And so this is where we're going. This is the diagnostic component of our nanoparticle development. And then, of course, if we had the high Z component, then we treat it with the X-rays and we'll get additional cell kill as well. It's always something that's very important to us. So there's lots of work being done in this area. And this is Antoine Van Owen from the University of Wollongong as well. So he's the Director of Molecular Horizons. And I just wanted to quote this. So there's plenty of room at the bottom, remember. So if you're a student and you're interested in this field, you've got some excellent facilities there. And over in India, of course. And so these kinds of things are available to you as well. You can study these nanoparticles, and going even further, going into single molecule biochemistry. So he's a physicist, of course, and he's developing these tools so they can understand how these protein machines, how they're working, drug delivery, and then, of course, in the environment they're in with COVID-19, viruses are very important. So he does a lot of work in that particular area. So we certainly have lots of facilities, lots of microscopes and things like that. So I'm not going to go into detail of that at all, but these are available on campus in the various research institutes. And we also have access to national research facilities just up the road as well. This is our reactor, Aggarwal reactor, which is up at Lucas Heights, just about 40 kilometres away from us, where we do a lot of our work for our detectors and things like this. And this is the Centre for Accelerated Science. So there were some previous talks earlier on in the conference about these. So we do similar sorts of things to understand how the charge collection works in our detectors and things like that. Very important. Some of the work that I do a lot is at the Australian synchrotron, where we're trying to get these very intense X-ray beams working as a therapeutic option for treating cancer. A little bit of motivation. So cancer incidence, according to the World Health Organization, is continuing to grow, of course, unfortunately. But we know that radiation medicine does play a very important role. About more than 50% of cancer patients receive radiation medicine as part of their cancer management. That's very, very important. And we're always trying to improve our quality of life. We're all living longer than we ever have. And so we want to make sure that life is living well as living longer. And then we've got these particular problems where we have survival rates of very aggressive cancers are quite poor. And so there's particular work that needs to be done there. So hopefully that provides you with motivation for working in these sorts of areas where you can make a contribution. So if I now take my head of school hat off and I put my CMRP hat on, if you like, Centre for Medical Radiation Physics. So is led by Director Anatoly Rosenfeld, who's a distinguished professor. And we have quite a big team there, of course, working on lots of different areas. And so I'm the head of one of these things, but we all work together. And so we can create this synergistic environment where we get lots of good outcomes. And so there's a lot of overlap between these different areas. We are an education, of course, and research centre as well. And so we train a lot of medical physicists that work both in diagnostic medicine and radiation oncology. So that's where our educational program is working very hard. So these are some of the devices and things that we work on. So we have here, Monte Carlo radiation transport simulations are very, very important. And so we use that in part of the development and quality assurance of our detectors. We have a focus on instrumentation, so not only the detectors, but we want to actually apply those detectors and have the readout systems as well developed in-house. And then, of course, TCAD modelling is very important in detector design if you're involved in this sort of area. And as I mentioned before, the ion beam induced charge collection, IBIC testing, is very, very important to understand how our detectors are working and what's going on there. So radiation damage is also very important. And most of our applications are in the clinical side, so in radiation medicine. You can see here we also do some work putting our detectors on satellites and things like this, because, of course, we all have an ideal plan to possibly one day go for manned missions to Mars and things like this, and just astronauts in general. And so radiation medicine is, of course, very important in a space radiation environment. And so we build detectors for that area as well. All right, so very briefly, what is dosimetry? I'm not going to go through all of this, but it's here if you need to know what it is. So basically determining the delivery of energy, okay, to matter. So in that case, usually we work with the absorbed dose, okay, where we're looking at the energy per unit mass, or it has the units of Gray, of course. So that's what we're usually interested in when we're trying to measure what's going on in our radiation environment. But in some cases, we need to debate not only the deterministic quantity, but also the associated stochastic term, okay? And I'll be talking a bit about that. So that's where microdosimetry comes into play. So why is it so important? Well, you can see here, this graph explains it really nicely. Okay, this is the response as a function of dose, so the irradiation dose. And you can see here the tumour control probability. So hopefully we get a 100% control probability. And you can see this curve going up here as we increase the dose. Obviously, if we want to minimise our normal tissue complications, the other curve here, the green curve, we want to try and minimise that. So you get this tiny little difference here between the two curves, and that's what we're trying to exploit, basically. And this is the advantage of radiation used to treat cancer. And so it's really why radiation therapy works at all. And so it's extremely important. And we're trying to broaden this gap, trying to widen this gap using our nanoparticles, or using different radiation environments, using whatever tools we have at hand, trying to increase that gap so that we still get our tumour control, but we minimise our normal tissue complications. Very, very important. So what are the challenges here then for our detectors? So this is like for any detector system. We're trying to make a tissue equivalent. So silicon, yeah, well, that's pretty hard. Unfortunately, humans are not a silicon-based life form. So unfortunately, the response of a silicon detector is not the same as the response of human tissue when it's exposed to radiation. So we need to make up ways in which we correspondingly measure the response of the silicon and convert it into a tissue dose. Very important. And then we have other things which are fairly common. The radiation dose rate dependence, total radiation dose lifetime is important. Radiation damage, dynamic range of the detector is very important. And obviously any isotropy in its response. And so this is why we need these smart detectors. So it's just not a matter of putting a lump of silicon in a radiation beam and measuring it. You've got to do all sorts of tricks and find special ways to satisfy all these requirements for a specific application. So this is one of the areas for external beam radiation. So we have got lots and lots of detectors that we've developed. They're all based on silicon. You can see here, and they all come in different sizes and shapes and things like that. And then once we have the basic design and tested, then we can go into production of some instrumentation that goes with it. So here's just an example of what's going on. So you can see here the instantaneous dose is being measured here in real time, okay, using our linear accelerator here, okay. And so each time the beam turns on, we measure a response from our detector. So this is our detector here, and it's sitting up in the head of the linac. And so every time you treat a little bit of the tumour, okay, and you change the angle. So this is the beam's eye view, basically according to what the head of the linac sees, because the patient is obviously sitting stationary. And so once we've done that, we get the instantaneous dose, and then we can measure the accumulated dose. So the total dose is measured here as well. So this is obviously changing the shape of these multi-leaf collimators, which are very quite new and being used in intensity modulated radiotherapy, okay, but also in VMAX, so volume modulated arc therapy. And then you've got almost more complications here associated with moving targets and things like this. So then we need to do quality assurance here. We need to get quantitative information, and so we can compare with other things. So this is in comparison with some film, basically EBT2 film. And so you can see we're getting a very nice correlation here. And obviously the resolution isn't great here because it's just a prototype. And so now we have a version of this which is not 11 by 11, but 256 by 256. Many, many more elements in this case, so we can get much finer resolution, which is working nicely. We're talking about internal radiotherapy. So this is brachytherapy. You can see here we're doing a similar thing here. We're treating prostate cancer with a high dose rate brachytherapy, so an iridium-192 source. And we have our detector system, which is sitting in the couch, in this case, sitting down here. And we can measure in real time, okay, what's happening. So as the source moves in through the needle, okay, there's 10 Curie source, so it's a very active source for a short amount of time. And then we get the total irradiation dose, which is then measured as well. And then finally here we can do it also for permanent seed implant brachytherapy. So this is where the radioactive sources are implanted inside the prostate. So you can see here, this is the prostate and the urethra running through it here. And you can see the red is where the seeds were planned to be, and the blue is where we measured the seeds to be. Okay, and so we get that nice correlation there. And so you can do this in real time. So if there is any mistake made, okay, they can do a replanning of the treatment, and they can adjust the position of the other seeds so that the whole treatment isn't compromised. And so this, again, improving the quality of life, improving the treatment outcome for the patient. Very quickly moving into, sorry about the speed, but hadron therapy. So hadron therapy obviously has big improvement over conventional X-ray therapy from a depth dose perspective. So we can deposit lots of energy here. So all the dose is being delivered at some depth, much deeper, and hopefully this is where your tumour is. Okay, and so you can deliver a very precise amount of dose at a very deep depth, and that way you can minimise the damage that's done to normal tissues which are sitting in front of your target. And so you can compare that with conventional X-rays, and you can't quite do that. So you have to do other tricks to make that work. And so that's the reason why hadron therapy is so popular, and there's having more and more hadron therapy centres opening up around the world. And so I can just go through this to explain that again. So we've got X-rays, all right? So we have to treat, so we've got all this splash, this dose wash, which is everywhere, basically, but we're still treating the tumour, okay? So it's very, very important. But with carbon ions, we can have much more conformal, is what we call, so we conforms to the shape of interest. And you can see here we're treating the scleroderma spine cancer very, very more precisely without any irradiation of these other critical organs and things like this. And so then we get lots of nice green here saying that we've saved all these organs. All right, so the difference, of course, is that the sparsely ionising radiation of X-rays is very different from the densely ionising radiation associated with ion therapy. And so the ion therapy, so the big difference is this RBE, the radiobiological effectiveness. So there's a whole form or area of physics and science, basically, which is understanding how this is working. And so we're moving into a completely different regime. So you can read about this in textbooks and things like this. So I'm not going to go through any of the mathematics here, but we're moving away from these deterministic sort of effects of dose. And this is dose, basically with distance into this region here, where we're getting more stochastic effects going on. So more probability and things like this. And so there's a whole area of mathematics and science which is used to understand what's happening here and to try and predict the radiobiological effectiveness of different beams, whether using protons or helium ions or carbon ions or xenon ions, all sorts of different types of ions that could be used. Radiobiological effectiveness is something which is very, very important. So you can see here it's quite complicated. You've got physical dose, biological dose, and then the clinical dose. So it's a whole world of science that needs to be understood. So our detectors, in this case, are trying to mimic a human cell. So this is a human cell with radiation going through it, a biological cell, and this is our small silicon volume, our small detector of silicon, which we're trying to mimic. Okay, so this is an array of these detectors have on a chip, okay, and then we can expose that to the irradiation environment. So the biggest problem here, of course, is not tissue equivalent, as I mentioned before, not a silicon form of life. So we've created these probes and things which we can work with very well. And so this is using the latest techniques, the growth techniques, in collaboration with our industry partners. So this is Syntep in Norway. And so we really want to do this extremely precisely, since this radiobiological effectiveness is one of the critical parameters in order to understand how the treatment's going to work. And it needs to be very, very precise. And so a lot of work has been done in that area by our group and many, many publications. And so you can just search and find the literature, which has been many, many publications there. So this is just an example in HIMAC. So this is in Japan, 400 MeV per nucleon, oxygen ions, basically. And so what we're measuring here with our detectors, we can measure this radiobiological effectiveness directly. So it's very, very crucial and very, very important piece of instrumentation. We can measure this as a function of depth as we go through okay, the Bragg peak, of course, and even beyond the Bragg peak. So that's a very, very important contribution to the field and something that we're quite well renowned for around the world. And finally, in the last few minutes, I think I've got about 5 more minutes left. I just wanted to talk quickly about these smart silicon detectors for synchrotron X-ray microbeam radiation therapy. So this is production of synchrotron X-ray beams. And so you can see here the synchrotron beam is another form of external beam radiotherapy, but it's very different from conventional radiotherapy. So this is intensity modulated therapy. And the main thing is we're delivering very high doses of 600 gray, okay, per fraction, which typically is 3 gray per fraction, and only a single fraction. So you can see here it'd be so much easier if we did unfortunately have cancer and we had to go to get treatment. Imagine just going for 1 fraction rather than 27 fractions. So treatment is very fast, but again, it's got to be very precise, and so that's extremely important that we make sure that we have the right quality. So the difference between the synchrotron beam, of course, is much lower energy. So you can see here it's about 100 keV energy compared to a normal LINAC. It's around about 1 MeV for a 6 MV photon field. And so again, there's going to have some challenges associated with that, because it's not very easy to produce an MV field with an MeV field from a synchrotron source, of course. So we're using our synchrotron beam, which comes out of our synchrotron. So we're using a superconducting wiggler, basically, to produce our synchrotron beam of X-rays. And that X-rays is then separated into these microbeams using a multi-slit collimator. So this is an air multi-slit collimator. And so we're producing these X-ray blades. Okay, so we're effectively doing X-ray radiosurgery is what we're performing when we're doing our treatments with this. And so our radiosurgery, so we've got these beams here. So these are our peaks with very few photons between our beams, initially anyway, but the dose rate is extremely high here. So we've got very high dose rates, very narrow beams. These are only 50 microns wide. Okay, and so we need to be able to measure the radiation dose inside these beams as well as in the valley region and do all of the quality assurance. And there's some very good, interesting radiobiological effects here going on as well. So we get very deep tissue penetration, which is what you don't normally get with these sorts of X-ray fields when you're using such low energy. So we've developed detectors, silicon detectors again, to measure each one of those microbeams. So we've got 256 strip detectors here, and they can measure the intensity of the beam in air for each one of these microbeams in real time. And so that if there is any problem with the beam, we can turn the beam off straight away. And I'm talking within microseconds, we have to obtain that information. And so that, again, minimises any potential harm you're going to be doing to patients or anything like that if there was something, unfortunately, to go wrong. And so when we're talking about these detectors, these are especially back-etched detectors. And so the window here has a thickness of about 10 microns. And so we need that because of the fact that this detector sits from in between the multi-slit collimator. So if I go back here, this is the multi-slit collimator that creates these beams, and there's nothing between here and the patient. If you have anything that sits in here, then obviously it's going to act as a scattering centre, and so we want to minimise any scattering, to minimise the total dose that's delivered to the patient, okay, in terms of scatter dose. And so that's what our detectors are doing here. So compared to a 375 micron thick detector, our 10 micron detector does nothing, which is ideal. Because if we're delivering dose rates of something like 20,000 gray per second, massive dose rates, then 2% of that dose rate is quite significant, scattering all over the room. Right, and then we also have some detectors here, so silicon microstrip detectors, and this is so we can do the overall quality assurance. So we want to do full dosimetry of our irradiation field, and this is a very, very challenging environment. Obviously, since we have very high dose rates, we have very steep dose gradients, and so we need a very large dynamic range. And so not only have we developed the detector, it's a waterproof detector, so we can put it inside a water tank or something like that, which is what they do in the hospitals, so it's standard quality assurance. And also the readout system and everything like that has been completely developed in-house, and the software. Very quickly, one example of that. So here we have our detector is green here, and we can scan that through our radiation field. And so we've done that here, and this is the output directly from our readout system. It takes about 12 seconds to do this. Okay, we're sampling at megahertz region, and this is on a log scale here. So you can see here 10,000 counts, 1,000 counts. And so this is a massive dynamic range that's required here. And we've got these extremely steep dose gradients. And so we can examine each one of these microbeams, these X-ray microbeams, these blades of radiation, which are used to treat these very difficult cancers. Now, the problem is, of course, our energy, this is our energy spectrum in blue, and the energy spectrum is sitting right here, looking at the mass energy absorption coefficient ratio of silicon compared to water, and you can see it's a very challenging environment. Because if we have any change in the spectrum between our peak and our valley region, in our photon spectrum, we're going to get a different response in our silicon. So that has huge implications for the dosimetry, and so it's very, very complex and something we spend a lot of time on. This is where our simulations come into play, so Monte Carlo simulations. So we've simulated the whole beamline, including the synchrotron production of the synchrotron X-rays itself. So this is the superconducting wiggler that I spoke about before. So the electrons come through here, they wiggle in the wiggler, of course, in the magnetic field, and then they go through the electrons anyway, go through the bending magnet around the synchrotron, and of course, the photons, though, they come straight through. And so we've modelled all of this, and this is just an example. So here we are, we're modelling, this is the steering angle. So this is, depending on the angle, the incident angle of the electron into the wiggler determines where the maximum flux is for the corresponding photons that are coming out. So that all needs to be optimised. We need to do that. So we're simulating our whole experiment Monte Carlo, so in radiation transport. Extremely important. And that's exactly what we do experimentally too, when we go and do experiments at the synchrotron. And so then we get these simulated microbeams, okay? So this is just a 3D plot of the dose as a function of depth here. There's a depth going down to 140 millimetres, and these are the microbeams here produced after the multi-slit collimator. And then we can zoom in on one of these, okay? We can take a cross-section of these and we can compare that with experiments. And so that's what we've done. And you can see here, the experimental data is fitting extremely well to the simulations. And we've still got some work to do down here, down in these regions here. And so that's ongoing at the moment. But this is some of the first time that this sort of work has ever been done before. And this detector system is the first one that's ever developed in the world as well. So, depth dose profile. So both in the valley region, so between the microbeams, you can see a very different depth dose profile compared to the peaks. And then we can get a comparison with our Monte Carlo compared with our detector system. So this is film and our silicon strip detector. So this was recently published in just last year. And then finally, my last couple of slides, basically. So we've embarked on going right the way through from bench to bedside, if you like. So these are not only doing in vitro experiments, but this is in vivo experiments in the first Australian image-guided long-term microbeam radiation therapy pilot study of the 9L glioblastoma. So this is brain cancer, very radio-resistant brain cancer, as I mentioned before, using the synchrotron beam. This is the irradiation setup, and here's one of our patients afterwards. So we need to follow them after they've had the treatment. And so it's very, very important. And so we've had a very, very successful outcome of a regime that we've developed, and including the quality assurance of the silicon detectors has been critical to that. After surgery, no permanent hair loss, so you can see here, no obvious skin erythema, so no skin effects, which is quite important. And then we have to study their eating habits, okay, cognitive, all this sort of stuff needs to be done, and certainly no induced cancers either. Right, but was it a 100% success rate? Obviously, no, it wasn't, okay? But still a very good result in the sense that the normal expected lifetime of these animals with a very aggressive cancer is only 20 days. And so if we can improve, can translate that into humans, then obviously even a 20% survival rate, long-term survival rate, is something which is very, very significant. Human form of this disease, the long-term prognosis is extremely poor, and you have a survival time of about 6 to 12 months once you're diagnosed. And so we have just recently published these results as well in scientific reports. Okay, so in conclusion, so real-time dosimetry in modern radiation oncology modalities is certainly very significant. and important. And we're going to need lots of detectors, not only silicon, but that's what we work in, silicon detectors for radiation medicine. And so we can maximise that impact and improvement. And then our novel silicon detector platforms can then be at the forefront to improve radiotherapy and improve different techniques, not only in radiotherapy, radiation medicine, so including radiotherapy and diagnostics. So I'd just like to thank some of my team members, okay, which are certainly worked very hard, and thank you very much.
Thank you so much, Professor Lerch. Am I audible?
Yes, perfectly
Hello,
audible.
can you hear?
Oh, yeah. Look at that famous picture.
Oh, all right. So, thank you so much. It was, I think, an understatement it would be to say that it was a very impressive talk. Your work is so fascinating, and I'm just amazed at the amount of science that is involved for imaging and diagnostics. You're literally traveling the world of medicine, biology, physics, simulation, instrumentation, and also technology, and ultimately linking it to society and medicine. So it's extremely fascinating and very glamorous also, and very impressive, the real-time detection, control, and the synchrotron. And I, for one, learned something new, a word called theranostics, therapy and diagnostics.
Good.
And also, I'm amazed at the versatility of things like silicon detectors. And I just wanted to say that later on in the day, we're going to hear from Professor Tsai on silicon detectors on display technology. So that's a totally different application altogether. So it's wonderful, and thank you so much for, we are very impressed, and I'm sure our students are also very fascinated. I have so many questions, but I think we better take some questions from attendees. So, Hitesh, taking the question. Are there any questions?
Good morning, everyone. There's one question from Martina Saran. The question is, are these detectors are commercially available? Also, how its dose response get affected by low energy and high energy ion beam irradiation?
Yeah, very good questions. So some of them are commercially available, and I mean, we're certainly open to research collaboration and things like that. We're in the process of commercialising some of these detectors through a spin-out company, which is in the process at the moment. But you can certainly talk to us, and we can have a conversation about if you want to do some collaborative experiments, or if you'd like to purchase some of these detectors, we're open to both of these. And then so the other question about the ions you're talking about, so yeah, so I mean, we're talking about a different regime here of detection in microdosimetry, if that's what you're talking about. If you're talking about a conventional silicon detector where we want to measure absorbed dose, then obviously it's very complex in the way in which you need to treat this between low energy and high energy. But if we're talking about microdosimetry, we're looking at event by event. So this is a different regime. And so from that perspective, it's immaterial what it is. It could be a neutron, it could be anything, because obviously when you're using ion therapy, it's a mixed radiation field in the actual body, of course. And so you're getting all sorts of other species being created and being detected. And so the principle of microdosimetry is you're not directly detecting the ionizing radiation. You're actually trying to detect the secondary irradiation. Okay, so you're using the sensor to sense it, but not to perturb the system. And so that's the key to microdosimetry, is you really want to sense the secondary radiation environment, not the primary radiation. So you don't want to be sensitive to that at all.
Any other questions, Hitesh?
Just a minute, ma'am.
There's a comment from an attendee which is very informative.
There's no any question, ma'am.
Okay, then I can ask my question. And it's just well, I guess it's, you must have got a lot of this in these days, so it's like the flavor of the day. So is there anything that you could do for the COVID virus with any of the work that you're doing?
Yes. Well, not directly at this stage. I mean, they have some of the drugs that we use, obviously, is just been reported to have a positive impact So that seems quite interesting. So one of these steroid drugs. But in terms of the radiation, we sort of had some discussion about what was done in the past for treating, doing whole irradiation of the lung and things like this as a small dose fraction and things like this. But I don't think this is really realistically considered as an option here. I think the development work that's going on in the biophysics and the virology sort of areas is really the area of speciality where we've just made so many advances. I mean, when I spoke to my grandmother when she was still alive, I said, what was the biggest impact on your life, you think? Because, you had the Industrial Revolution and things like this. And she said, no, it was penicillin. Okay, penicillin was just the greatest invention in her generation. So I think these sorts of things, it's coming, it's going back into this phase again. So if we have these nasty viruses which are hanging around, we need to concentrate our efforts. But physics plays a huge role because, as I said, with the biophysics area we have here, they need us to develop these instruments, okay, so that they can understand how these systems work. And it's really down these electron microscopes, these cryogenic electron microscopes, which is what we have here, play a really important role. And so, they need lots of young physicists with good brains. Unlike mine, my brain's too old, okay? But young physicists, they have great minds and combine their knowledge with chemists and biologists, and that way you'll achieve some great things.
And finally, this is a non-technical question of sorts, because a lot of young students are listening to you. How did, from your own experience, how did you manage to get into so many areas? I mean, would you encourage people, because people tend to be rather narrow-minded in their subject, but in order to do this level of research, you have to know so many things. So is it doable, or only you have to be a very smart learner to actually get down to this?
It's a really good question, and something students should ask. It's a little bit of a trap, I suppose, is to say too focused sometimes. I think try and experience the world in the sense, don't be afraid to make mistakes, okay? Something that's what us researchers do all the time. I mean, 90% of the things that we do don't work, okay? And sometimes that can be very discouraging. And so I think you've got to appreciate that we can't know everything, and I don't pretend to know everything. There are other experts. You can see the size of our team. We've got a big team of people that we can plug into. So the network of people is extremely important. And so that's why these sorts of environments are fantastic. All right, it doesn't cost anything for me to give a talk here, and we can have these interactions and things like that. Eventually, obviously, it's better to have a one-on-one face-to-face interaction, but that can be done later on, okay? And so I think the students should concentrate on trying to broaden their knowledge a little bit, okay? And don't be afraid to go into disciplines where they're not experts at all, okay? Because you've got to appreciate from the other side, somebody else has to be willing to try and talk to you and communicate with you when they may have never done physics in their life, okay? And so it's something that you need to be quite conscientious of, okay? And so if you're polite and you understand what sort of environment, and that's the interesting part of multidisciplinary environments, the respect you have for each other in their respective fields, and then you can absorb the knowledge, you start to absorb that knowledge. So, but you've got to have the courage just to go into that environment in the first place.
Thank you so much, Professor Lerch. It is wonderful to have you. And I'm sure our students are taking note of everything. So let's move on to our next speaker of the day. And we have Professor Atul Khanna from the Department of Physics, Guru Nanak Dev University, which is in Amritsar, Punjab. And I'll just briefly read his biography. Professor Atul Khanna has about 25 years of experience in studying structure property correlations in oxide glasses, nanoparticles and thin films using X-ray and neutron diffraction. Mass NMR, which I just Googled to find out is magic spinning or something, and optical and Raman spectroscopy. And after earning his master's in physics from Indian Institute of Technology, Delhi, he worked as a Scientific Officer in the Technical Physics and Prototype Engineering Division of Bhabha Atomic Research Center, Mumbai. And his PhD is from Guru Nanak Dev University in Applied Physics. And he's also done postdoctoral research at the University of Arkansas and published over 85 research papers in very good journals, has 10 students who've earned their doctorate degrees, and 6 more currently enrolled with him. And he's been honored with the Young Scientist Award in Physics and many others. And we're also happy to hear that Professor Atul Khanna loves teaching. And besides the conference presentations, he has delivered popular talks in Inspire camps at several schools, colleges, and universities, which we think is so important. Today, he'll be talking to us on synthesis and characterization of rare earth, dope, tungstate, and molybdate bulk and thin film materials for light emission applications. Professor Atul Khanna, welcome, and please deliver a lecture.
Thank you, Professor Venugopal, for my kind introduction. Can you hear me?
Yes, we can hear you.
Thank you very much for my introduction. And I congratulate and compliment the Guru Gobind Singh Indraprastha University for organizing this symposium on smart materials. And the focus is on their applications. So we have a variety of materials which are used for gas sensors, for light emission devices, for optoelectronic sensors. So this symposium is really very relevant. And I thank the organizers, in particular, Professor Rajesh Kumar, Dr. Venugopal, your Vice Chancellor, Registrar, and Professor Tyagi for this kind invitation. And I have prepared a presentation which is can you see the screen?
We can't see your screen.
So there's an option of share content just near to the video button.
Okay.
The bottom panel,
Yes.
share content.
Can you see
Yes,
now?
I think, yes, it's coming. Yes, we can see. I think we can go to slideshow. Yes. Thank you.
Is it clear? Can you see it clearly?
Yes, we can see it clearly.
So this is the title of my presentation. I will be speaking on calcium tungstate and calcium molybdate materials, both in the bulk form as well as in the thin film form. And we characterize these materials by X-ray diffraction to determine their crystal structure and their short-range structure, in particular the bond lengths and the local environment like coordination number. And our interest is, of course, in the luminescent properties of these materials, the photoluminescent properties. So I am, of course, from physics department at Guru Nanak Dev University in Amritsar, Punjab, Northwest India. You can see the picture of our campus. The main building at the center is our central library, and the physics department is on the left-hand side of this building. I hope you can visit Amritsar in the near future. It will be a pleasure to host all of you. So as I said, this presentation is on calcium tungstate and calcium molybdate phosphors, light-emitting materials. And we dope these materials with rare earth ions. I will describe the results on the structure, crystal structure, and short-range properties and their luminescent properties while doping these materials with europium, dysprosium, and erbium. So we do structural characterization of these materials by synchrotron X-ray diffraction studies. The synchrotron X-ray diffraction studies were done at Indus2 Synchrotron at Radharamana Center for Advanced Technology at Indore in India. And then we carried out neutron diffraction measurements on some of these samples at Bhabha Atomic Research Centers. And some of the measurements were also done at Budapest Neutron Center at Hungary. So we have used Raman spectroscopy and photoluminescence spectroscopy. Raman spectroscopy we use to understand their short-range structure, and photoluminescence spectroscopy to study their light emission and down conversion properties. And then we prepare their thin films by pulse laser deposition technique. So what are the main results? In fact, one of the main focus of our X-ray diffraction studies was to answer one question which remains unresolved in these materials. And that is, when you add these europium, dysprosium, and erbium ions, do they replace calcium sites in the structure, or do they exist as a separate phase in the material? That means, are we having one phase materials, or are we having two phase materials in these materials? So that was the question which could be answered by only synchrotron X-ray diffraction measurements. So how we prepare these materials? Synthesis is done by using sodium tungstate, which is soluble in water, and we prepare another salt of calcium, which is also soluble in water. So you prepare calcium nitrate and sodium tungstate aqueous solutions and mix them. So you get calcium tungstate as precipitates and sodium nitrate, which is soluble. So simple filtration will give you this wonderful material, calcium tungstate. It is a very good phosphor material. And calcium tungstate precipitates are washed, and you dry them around 80 degrees Celsius, and you obtain nanoparticles. Typical size of the nanoparticles as measured by X-ray diffraction and by SEM analysis is around 30 nanometers to about 35 nanometers. And then you add rare earth oxides. So the rare earth oxides that we use are europium oxide, dysprosium oxide, and erbium oxide. And we use europium oxide in the concentration range of 1 to 10 mole%, and dysprosium oxide also in the same range from 1 to 10 mole%. And after you mix these materials, we heat them to high temperature of about 800 degrees Celsius, and you obtain the material. And the question that we want to answer by X-ray diffraction, by neutron diffraction, is whether we are having a single phase material in which the calcium sites are replaced by the rare earth ions, or do we have a two phase materials? Is there a phase coexistence, or you get a one phase material? So this question is very important to understand their luminescent properties. So these are the FESM images taken with a field emission scanning electron microscope. So the nanoparticles are having this spherical morphology, spherical particles you can see. And in the inset of the image on the left-hand side, we see a blown up picture of one of the particles. So we see a highly porous structure, and the typical size of one spherical nanoparticle is several microns. And when you heat it to about 800 degrees Celsius, these spherical particles, they break down and they form more irregularly shaped particles, which is visible from the FESM image on the right-hand side. We do the EDX analysis, energy dispersive X-ray analysis, to determine the composition of these materials and whether any segregation takes place for the rare earth ions, and what is the sample composition as compared to the nominal batch compositions. So when you do the EDX mapping analysis, we see that the concentration of the calcium, tungsten, oxygen, and the rare earth ions is fairly uniform. At one point, you measure a calcium atomic percent of about 11%, At the other point, it is 9.75, 12.6. And these differences are within the limits of experimental uncertainties. So the average calcium atomic percent is 11.06. And that agrees fairly matrix, and same result we obtain for the calcium molybdate materials also. And the elemental composition of europium and other rare earth ions, it agrees very well with the nominal batch compositions. And in fact, we also determined the elemental composition from reticle analysis of the X-ray diffraction data. So that was also showing very good agreement. So samples are prepared in a fairly well, and they are having uniform distribution of rare earth ions. So the question that we want to answer, the unresolved question in these materials is, do europium, dysprosium, and erbium ions replace calcium ions in the tetragonal crystal structure, or do they exist as a separate cubic phase? Europium oxide and the other rare earth oxides, they have cubic crystal structure, whereas calcium tungstate and calcium molybdate has tetragonal crystal structure. And many people have done X-ray diffraction studies on these materials. And in fact, the Bragg peak positions of cubic rare earth oxides and tetragonal calcium tungstate are very close to each other. And if you use a laboratory X-ray diffraction system, you cannot resolve these peaks. And moreover, in your laboratory XRD system, you have copper K alpha 1 and copper K alpha 2 X-ray lines. And the peaks are broadened, and the peaks of rare earth oxides and tetragonal phase of calcium tungstate or calcium molybdate, they mix, and you see very broad peaks, and not possible to resolve them and answer the question whether the calcium ions are replaced or whether there is a phase coexistence. And there are in fact erroneous results in the literature that the calcium ions are replaced by the rare earth ions. And these results, these conclusions, they have derived from using low resolution X-ray or neutron diffraction measurements. So there is a need for synchrotron high energy X-ray diffraction experiments to answer the question. So we did these experiments at our third generation synchrotron, Indus 2 synchrotron at Radha Ramanna Center for Advanced Technology, RRCAT at Indore. So Indus 2, as you know, is a third generation hard X-ray source. Maximum energy of the beam is 2.5 giga electron volts. You can see a picture of the circular building which houses this storage ring and the synchrotron. And we use the angle dispersive X-ray diffraction beam line, which has a double crystal monochromator. And the wavelength used was lambda was 0.78681 angstrom, highly monochromatic and intense X-rays. So you get very sharp X-ray peaks, and the diffraction pattern was recorded in the transmission geometry using an image plate detector. These are the X-ray diffraction patterns. In the first graph, on the top graph on the left-hand side, the bottommost trace is of calcium tungstate nanoparticle sample. You see broad peaks. Now here along the x-axis, we have plotted d-spacing, not the angle 2 theta. And you see the first sample, which is a nanoparticle sample with a particle size of about 35 to 40 nanometers. The peaks are broad, and when you anneal the sample, the peaks sharpen because of the increase in the size of the crystallites, and also the peaks, they shift towards lower D values. So there is some kind of a compression which takes place on the crystal lattice when you do heat treatment. And when you add the rare earth ions like europium or dysprosium, the peaks again shift towards the longer D values. So there is a tensile stress which is arising, and that tensile stress is not due to any replacement of the ions because the peaks of the cubic oxide phase, they are detected distinctly. So the two phases, they coexist, and there is no major substitution of calcium ions in the tetragonal crystal structure. So same features we observe with dysprosium, with europium, and also with erbium ions. We do ritual fitting using full prof program, and I show you in this picture the peak fitting done with the Rich-filled program, and we have to incorporate 3 phases in order to get a good fitting of the X-ray data, X-ray diffraction data, and you have to incorporate calcium tungstate tetragonal phase, europium oxide cubic phase, and also cubic dysprosium oxide phase to match the refined X-ray diffraction pattern with the experimentally measured X-ray diffraction pattern. So the samples are composite materials, and they are 2-phase materials or 3-phase materials. There is little or no substitution of calcium ions by the rare earth ions, and you can once you do the ritual fitting, you can determine the lattice parameters, the unit cell parameters A, B, C, alpha, beta, gamma, and also the coordinates of the atoms, in the lattice, and you can determine the short range structure. So the W ions are having the tetrahedral coordination, whereas the calcium ions are having the octahedral, they are having the coordination number of 8. And we also determine the bond lengths. So the W oxygen bond length lies in the range of 1.77 to 1.80 angstrom. And the W oxygen bonds are almost equal to the bond angles in the tetrahedral configuration, that is about 107 degrees. And the W oxygen coordination number is 4, so it is in tetrahedral coordination. In the calcium oxygen, for the calcium oxygen bond lengths, the values are 2.44 angstrom, and there are in fact 2 types of calcium oxygen bond lengths. One which is in the range of 2.39 to 2.44 angstrom, and the other second type of calcium oxygen bond lengths are slightly longer in the range of 2.43 to 2.46 angstrom. And calcium is having a coordination number of 8, so that agrees very well with the theoretical predictions. And these are the lattice parameters. Calcium tungstate is tetragonal. Calcium molybdate is also tetragonal. Europium oxide is cubic with a lattice parameter A of 10.788 angstrom. And its mole percent calculated from Ritual analysis is 9.1, whereas the nominal batch composition was about 10 mole percent. So good agreement, fairly good agreement with the batch compositions and the values determined from the X-ray diffraction analysis. We also carried out neutron diffraction studies at the Bhabha Atomic Research Center in Mumbai, and also some measurements were done at Budapest Neutron Center. So the resolution of neutron spectrometer is less as compared to the resolution of a XRD system. So the peaks are more broader, but the result is same, that the materials are 2-phase materials, and we calculate the pair distribution functions from the Fourier transform of the structure factors, and the peaks in the pair distribution functions GR give you the probability of finding the atoms at a particular distance from a reference position. So you see that the first peak, the bottommost trace, calcium tungstate 80, the first peak is at 1.71 angstrom, and this peak is existing in all the samples and these peaks are due to W oxygen correlations, the W oxygen bonds. The second major peak is at around 2.84 angstrom, and this peak is due to oxygen-oxygen correlations. So if you measure the X-ray diffraction patterns and then you do the pair distribution function analysis, you will find this second peak around 2.8 angstrom is missing because the X-rays cannot detect the oxygen atoms because of the weak scattering of X-rays from low Z elements like oxygen. Whereas neutrons are very good for finding the structure of oxide materials because they can determine the oxygen atoms also very accurately. I'm seeing some questions which I will address at the end of the presentation. So these are the surface morphologies of calcium molybdenate particles doped with erbium oxide, and the particles are fairly big, and we also see some kind of a morphology which is having some definite angles. So these are the morphologies of calcium molybdenate materials doped with erbium oxide, which shows both up conversion as well as down conversion. So in an up conversion process, you convert the long wavelength light like 980 nanometer to green light, and whereas in down conversion, you shift the UV light, you convert the UV light like 380 nanometers light to green light, which is having a wavelength of about 560 nanometers. X-ray diffraction again confirms two-phase materials in erbium oxide doped calcium molybdenate, and we determine their structure from the Ritwell analysis. Calcium oxygen is again in having a coordination number of 8. The coordination number of molybdenum ions is 4, and erbium oxide is having a cubic structure. Calcium molybdenate is of course tetragonal. You can see details of this paper in Actocrystallographica, which will soon appear. And we did the Raman measurements of calcium molybdenate as well as the tungstate samples. This is the Raman spectra of calcium molybdenate samples doped with erbium oxide. And we see several sharp peaks because of the crystalline nature of the samples. For the sample which is annealed at 80 degrees Celsius, the peaks are broader. But as you increase the annealing temperature to about 800 degrees Celsius, the peaks sharpen. So there was a question from audience that what is the power used during these Raman measurements? These Raman spectra were measured at an excitation wavelength of 514.5 nanometers generated by an argon ion laser. And the power of our laser, maximum power is about 25 milliwatts. But when you actually do the measurements, we use a power level of about 10% of this laser power. That means 2.5 milliwatt is the maximum power that may be incident on the sample. So it is few milliwatts, the laser power which is used during Raman measurements is 1 or 2 milliwatts. The maximum power of the laser which we have, the argon ion laser, is 25 milliwatts. And this is the Raman spectra of calcium tungstate samples doped with europium. All these peaks, they are due to the W oxygen bond vibrations. We don't see any peak due to europium oxygen bond vibrations. Probably the europium oxygen peaks because the europium oxide concentration is small. It is maximum concentration is about 10 mole %. And moreover, W oxygen bond vibrations are much more strongly Raman active than europium oxygen bond vibrations. And this is the luminescence spectra of europium doped calcium tungstate samples. And we have varied europium oxide concentration from 1 to 10 mole %. And the red curve is for 1 europium oxide, 1 mole % europium oxide. The green curve is for 10 mole % europium oxide. And also in the inset, you can see the expanded graph in the wavelength range from 610 to about 618 nanometer. So you see, as you increase the europium oxide concentration, the intensity of luminescence increases, and it reaches a maximum at a europium oxide concentration of 3 mole%, and beyond that, from 5 to 10 mole% of europium oxide, the photoluminescence intensity falls. This is due to concentration quenching effects. And all these, so europium emits very strongly in the red part of the electromagnetic spectrum. So you can get red phosphors by doping with europium oxide. And this curve tells you how the intensity of photoluminescence of europium line at 615 nanometer varies with rare earth oxide concentration. Intensity for europium oxide is maximum at 3 mole%, and with dysprosium oxide doping, the intensity of photoluminescence yield decreases continuously. So much more stronger quenching effects are visible in dysprosium oxide doped materials, and dysprosium emits green light, which is centered at 575 nanometers, and europium emits strongly in the red part of the visible electromagnetic spectrum. These are the coordinates, the color coordinates, which we determine for the samples. The color coordinates give you a measure of the color which is emitted by a phosphor. So if a material is emitting green, blue, and red color equally in same percentage or in same proportion, then it is a white light emitter, and its color coordinates will be 0.33 and 0.33. X coordinates will be 0.33 and Y coordinate is also 0.33. So it will be located at the center. So that is an ideal white light emitting materials. But if it is a red light emitter like europium doped samples, it will emit more strongly in the red region. So its X coordinates will tend towards 0.6 or 0.7. So the white light emitters, they are at the center. The green light emitters will be at the top. The blue light emitters will be at the extreme left, and the white light emitters are at the center. So these color coordinates are often used to denote the color purity which is emitted by a luminescent material. We have also prepared their thin films, because if you want to miniaturize a device, thin films are better materials. They are for miniaturization, thin films are better materials. So the best technique to prepare their stoichiometric compositions is pulsed laser deposition, where we use a pellet as a target. The pellet is doped calcium tungstate or calcium molybdenate, and we bombard this target with excimer laser pulses. And excimer laser, it lasers in the UV region at a wavelength of about 250 nanometers. So the pulse width is only a few nanoseconds or even less. So very large energy is given to the target in a very short time, and whatever is there in the target that comes out, it ablates out, and the vapors are condensed on the substrates, and you get thin film deposition. So we prepared the thin films of calcium tungstate, calcium molybdenate, doped with rare earth ions on quartz substrates. And during deposition, you give you heat the substrates to a temperature of about 650 degrees Celsius in order to get crystalline phase. So we get films which are again tetragonal phase. And in these materials, in the thin film form of the calcium tungstates, these are one phase materials, and the dysprosium ions are actually doping. They are entering the crystal structure of calcium tungstates and calcium molybdenate. And the films are also highly textured. That is usually a feature that thin film materials are more strongly textured. That means there is a growth of the thin film along some particular orientation or some particular direction. And thin films also emit, again, in a similar fashion. The europium materials are red light emitting materials. And if you co-dope your samples with europium and dysprosium, Then you get white light emitting materials. Their color coordinates are at the center with a color, and the color coordinates are about 0.33 and 0.33. So I summarize the crystal structure and short range order of calcium tungstate and calcium molybdate in the bulk form, and in the thin film form is characterized by X-ray diffraction. And we unambiguously answer the question that europium, dysprosium, and erbium ions, they do not replace the calcium sites in the tetragonal crystal structure of bulk materials. And rare earth ions, they expand the calcium tungstate lattice. 3 mole% of europium oxide gives maximum luminescence in calcium tungstate. Luminescence intensity decreases with the increase in dysprosium oxide concentration from 1 to 10 mole% in calcium tungstate. And you get white light emitting materials which can be used for fabricating white light LEDs by using europium and dysprosium co-doping. Erbium, europium, and dysprosium co-doped calcium tungstate and calcium molybdate thin films can be prepared by pulsed laser deposition with very good stoichiometry. Intense red light emission on europium doping, and erbium and dysprosium produce white light emission, and calcium molybdate is a better luminescent material than calcium tungstate. Thank you. Thank you very much for your attention.
Thank you very much, Professor Atul Khanna. Am I audible?
Yes, madam. You are audible.
Yeah. So, thank you so much. That is such an interesting talk. The study on tungstates and molybdates in bulk materials and in thin films. And I'm quite impressed with the way you started with the limitations of normal XRD, and then you have to use stronger, harder X-rays, and then get higher resolutions and synchrotron radiations, neutron diffraction, and so on. And also simultaneously you had these simulation studies which corroborated what you found experimentally, and actually found out these structures, and then all the photoluminescence and light emitting properties. And I'm sure a lot of our faculty would resonate with some of this work, because there is work going on in our department also. I think people are already submitting questions. So Ritesh, maybe you can tell us if there are questions.
Yeah, any question or any comment is welcome. Please.
Yeah, there is one question from Lomas Rishi.
Yes.
Although there are many dopants, why you have doped dysprosium and europium only?
Actually, dysprosium is a white light emitting material. It emits strongly in the green part of the electromagnetic spectrum, and it also emits somewhat in the blue part of the visible light spectrum, whereas europium emits most strongly in the red part. So if you co-dope with dysprosium and europium, you get a material which is a good white light emitter. So you get blue and green emission from dysprosium ions and red emission from the europium ions. So the net result is that the sample is a white light emitter.
And one more question from Ashutosh Anand.
Yes.
In real life, where we can use these nanoparticles?
So you can use them as luminescent materials in your LEDs. LEDs normally, of course, use PN junctions where they employ semiconductors. But we can also use these materials like erbium doped calcium tungstate or molybdates as UV sensors. So erbium shows the phenomena of down conversion and also up conversion. It can convert UV light to visible light. So we can use it as a UV sensors, and we can also use it as light emitters.
There's one more question from Dr. Karthik. Which one
Yes.
nanoparticle or thin film is more effective in LED applications?
We have found that between calcium tungstate and calcium molybdate is a better material. Its luminescence intensity is almost 3 times higher for all the samples with all the dopants.
Thank you, sir. There's no more question.
Thank you.
Thank you so much, Professor Atul Khanna.
Thank you,
I
Dr.
heard you say,
Venugopalan. Thank you.
I just had one small question. You talked about down conversion and up conversion. So
Yes,
I gathered that the processes are nonlinear processes happening in.
Actually, they are not really nonlinear phenomena, but they are involving more than one photon at a time.
Okay.
So,
Okay. Usually in quantum optics, they're understood as nonlinear when you have down conversion and up
yeah, maybe
conversion.
they are. I am not very sure about the whether they are.
They could be.
Yeah, maybe they are.
Yeah.
Yes.
Maybe they are. Yeah. Thank you so much. It was very interesting. Thank you.
Thank you.
So let's get on to our next talk. Our next speaker is Professor P.V. Sahare. And Professor Sahare, I think, is a familiar name in our department. He's visited us many times. Let me just read out a brief biography. Professor Sahare is presently working as a faculty member in the Department of Physics and Astrophysics at Delhi University. He was also a faculty member at Nagpur University and the University of Pune. He obtained his master's and doctorate degrees from the RTM Nagpur University and has obtained various prestigious fellowships, including the National Overseas Fellowship for UGC and CSIR Research Associates. Did his postdoctoral research from the Department of Culinary Science and Engineering at the University of Massachusetts in Amherst. He has guided more than 15 PhD students and successfully executed 10 research projects sponsored by the DSC, IUAC, DRDO, and University of Delhi, and published more than 100 papers. He's a recipient of the IAAM Advanced Material Scientist Award in 2011. And for his research work, he has close associations with Lebedev Physical Institute in Moscow, GINR at Dubna in Russia, and the Kyunghee University in Seoul, South Korea. His area of interest include nanomaterials, luminescence spectra, radiation dosimetry, organic lasers, gas detectors, and optical sensors. And he's associated with the Luminescence Society of India and the Nuclear Tract Society of India. And we look forward to hearing his talk on nanomaterials, synthesis, and application. Professor Sahare, please.
Am I audible?
Yes, sir, you're audible.
Okay, and visible too?
Visible too, yes.
Yeah, but I do not know how to share my screen over here.
You can look at the bottom panel of your screen.
So a little bit some technical problem, so I don't know how to solve. Can some help from your side, please?
Maybe Amar or somebody can just explain this, sir.
Yeah, so this sharing is disabled over here. The sharing of the screen is disabled.
Okay, the share screen is disabled.
I cannot share my screen.
Hello, technical team will sort it out for you.
Yeah, please.
So please hold on.
Our technical team will sort it out.
There's a button just beside the video button. It's called share content.
Yeah, it's a disabled.
Even assigned us.
It's disabled and I cannot enable it.
Actually, I think it's disabled for everybody. Probably.
Now it's able.
No, I'm not sure. No, I cannot.
So in the left corner, there is a file, edit, and share option. Share, just above it. In the menu bar, share. File, edit, share.
File edit share is not there. I couldn't see it.
Top left. In the menu bar.
Top left. No, I'm sorry. Can't do anything. So
So,
maybe I can take some help from. It's still disabled. I cannot. When I click on this.
sir, you are the presenter of this session.
Yes.
You have been able
Yes.
from our side.
No, but from my side, it's I cannot. I'm clicking on that, and nothing happens. So it's not shows open system preferences. I don't know what it means, and I don't know too.
I think if you go from, are you on the grid mode? Are you seeing the grid?
No,
This top right panel.
top right also nothing.
This is option called file, edit, share, view, communicate, participant. It's an option of share also.
Yeah, that is disabled. That is what I'm saying. Share content is disabled. So when I click on that, nothing happens. That's the problem.
So I think there's a problem in your WebEx, I think, because we have able from our side.
Okay. So I don't know what to do. Maybe I can take some help from my son.
Maybe you can join again. I don't know.
Yeah,
Rajesh,
yeah, Anu ma'am.
Rajesh, you can take me.
Can we invite the next speaker?
Well, he would also need to share. Let's give him 2 minutes if he can fix it.
Okay.
Otherwise, we can go to Professor Tsai.
Okay.
No problem. So just
Share नहीं
in 2 minutes.
allow नहीं करेगा. So my son says it's disabled and not allowing. So do I need to join again and then you can see, or what? I don't know what to do. How to solve the technical problem? I don't know.
Because we have able from our side. You are the presenter for this session.
Yes.
Amar, when you change the view, it seems to come on. Like when I change from grid view to another view, then the share content works. Sometimes I don't know why it's doing that.
Right now, the presenter is Professor Sahare sir only.
Okay. Can you remove him as presenter and put him back again and see if it works?
Yeah.
Just do that once more.
नहीं वो लीव नहीं कैंसिल कर.
Otherwise,
तो चलेगा नहीं. तो लीव करके दोबारा से ज्वाइन कर ले.
ये कर सकते हैं और you can reset this.
Fine. You are now the presenter. Now it's okay. Now
Okay, fine.
Okay. Yeah. Okay. तो कहाँ है मेरा वो ये यहाँ होगा. डेस्कटॉप कहाँ पर आएगा. स्क्रीन कहाँ से. नॉर्मली ऑल ये इसको एक करके ऐसे.
Your screen is being shared. Yes, आ गया sir.
Okay.
You can go to slideshow.
Okay, thank you.
Please go to slideshow.
Okay.
Yes, it's perfect now. Yeah.
Screen.
Yeah, please go ahead.
I think it's resolved now. Okay.
Yeah.
So at the outset, I must thank Dr. Rajesh Kumar and his team at IP University who who has given me a chance to or opportunity to present my work over here. And I must congratulate and compliment for successfully this organizing this international, I think, e-conference, what it is called. At the same time, I must thank Dr. Shruti Aggarwal and Professor Mahesh Verma, your Vice Chancellor, for again this opportunity. So I will be today talking about some synthesis and applications of some nanocrystalline materials. What I have done in my presentation is I will not discuss much about characterization and this thing, but more concentrate on synthesis, because the material synthesis is very important, whether it is nanocrystalline, single crystal, or microcrystalline. So what I have done is I will be discussing many different kinds of synthesis techniques or methods in during this talk. So this is the outline. So introduction, different methods, and little bit work that we have done in our laboratory. So as you know that nanomaterials, they exhibit enhanced optical, electronic, and structural properties. They could be used for many applications: energy harvesting materials, drug delivery. They are in last this talk also we have seen that they are very efficient phosphors for display applications and LED applications. These luminescent materials could also be used for biological labeling, and they are good TLD and OSLD materials. And we found that these nanomaterials could be used for this radiation dosimetry, and they can measure very, very high doses. We are the first to investigate this kind of thing, and got good recognition for that. Then these materials could also have different applications for sensors and detectors, and therefore they are very, very important kind of materials. But at the same time, for some applications you need powder form, for some applications you need in thin film form, and so on and so forth. So the morphology and this form of whether it is powder and film and all that matters. Okay, so therefore the techniques of synthesis also, they vary depending upon your morphology, and kind of application. So this is for the sake of just completion. This nanomaterials, you know that they could be in powder form, they could be in powder form, nanoparticles, nanowires, nanorods, and so on and so forth. Then they could be thin films and colloids and quantum dots, and so on and so forth. The very important thing about the nanomaterials are when you go from the bulk material into nanomaterials, the surface area increases, and there are some applications where this surface area is important, surface defects are important, and therefore they become very important. Also another property is quantum confinement, and also you can tailor the band gap, because it is believed and it has been proved that when you go from bulk or microcrystalline to nanocrystalline, the band gap widens, and therefore also for some applications they are very, very important. So this again slide shows that how the surface area will go on increasing when you cut them into more and more pieces. And also in quantum confinement, the shape of these bands also varies, and that is also very important for some applications. So again, there are two approaches. One is top-down, where you go on breaking these bigger molecules into smaller. So mechanically also you can, but nowadays then if you want to go to nano, then there are some kind of these machines called ball milling machine. So by that you can go on breaking until you get nanomaterials. We also applied and studied some such kind of nanomaterials. There is another kind of approach, is a bottom-up approach, and in this approach that you really tell, you can control the morphology, control size, and so on and so forth. You can make them in powder form, you can make them in film form, and so on and so. So therefore, another approach is very, very important in case of these nanomaterials. So these are some of the methods also of the synthesis. So I will be discussing the methods of synthesis in my talk today. So for powder and for thin films. So this is again the bottom-up approach where you have a chemical co-precipitation. That method we have just listened in the last talk also. Then we have hydrothermal method, sol gel method, thermal plasma method, combustion method, and so on and so forth. For films, we have used sputtering method and chemical vapor deposition. Also, we have developed this facility in our laboratory, and in Rajesh's lab, there is this template-assisted electrochemical deposition. So I will be discussing some of these methods of synthesis in my talk, and also, of course, ball milling, that is the top-down approach. So therefore, I will not go into much characterization and also much applications, but focus more on the synthesis of these materials. So what happened in 2000, around 2005, when we didn't have much funds in our laboratory, so we didn't know what to do, and nano, this was booming at that time. So we thought, why not find out some kind of method so we can study some nanomaterials also. And in the literature, we found some papers where just by simple co-precipitation methods also you can synthesize nanocrystalline. So my first paper that appeared on this nano CaSO4dy is well-known, this TLD material for measurement of radiation. And we found that in this, when you go down to the nano size, that the sensitivity of this material to radiation by this particular technique, thermoluminescence technique, that decreases. But at the same time, radiation, that those measurement span that very much increases, and you can measure. Generally, you can measure this by microcrystalline this form. You can measure up to around 100 gray. But with these nanomaterials, you can go up to maybe 10⁻³ in kilo gray, or in one of our materials, we also have measured into mega 10⁵ gray, and so on. And the materials, we have found that they are very, they are not very susceptible to, or properties do not change by giving too much radiation. So there is not much radiation hardening also, and therefore they have very good applications. And this is another paper where we also have wanted to study whether there is an effect in this particular material. There is a phase transition. So whether there is an effect of phase transition on this luminescence properties. Again, this sample or material is synthesized by a very simple co-precipitation method, where we have taken CaCl2, KCl, and then dropwise in a ethanol and H2O this as solvent, and we have put dropwise this ammonium sulfate, and then K2Ca2SO4 thrice this compound forms, and then we can dry it and give different heat treatments and all that, and we can use this. So this is the method. So when people they say, or in nano, it's very expensive, and this thing, I would say that the method, some of the method of synthesis are very, very simple and very inexpensive, and therefore the only thing over here may be characterization, because there you need more sophisticated instrument. So otherwise, research in nano one can do with very less funds also. So in this material, you'll see that we have synthesized this in this form, nano rod form. Okay, this shows, and then we anneal at different temperatures, and at high temperatures, of course, they agglomerate. But the nanorods also break, because the initial phase is orthorhombic, and then when you anneal, it goes to the cubic phase, and therefore there's a stress, and these nanoparticles breaks also. So this the XRD pattern shows. This is in orthorhombic, and then this is in cubic form. So there is a phase change, and with this phase change, you can see that all the glucose structures also they change. This study is very, very important, because any kind of change in glucose structure or this, because using the area under the curve or this peak height only, so we determine the doses, radiation doses, and therefore any change in this kind of this thing, and also we heat and cool several times this material while reusing, and therefore it is very, very important to do such kind of study. Then this same technique, I have chosen this K3NaSO4 twice. This is another material deliberately I have chosen, because in the technique is the same, but the important in of this material is that here your ingredients K2SO4, Na2SO4, they are soluble in water. At the same time, K3NaSO4 twice, this is also soluble in water. So we didn't know what to do when the your starting material as well as the product, both of them, they are soluble in that solvent to what to do. But then we found the solution that if you put this ethanol, go on increasing the quantity of this thing, the solubility of this material in over here decreases, and therefore at some point of that concentration, then it starts precipitating, and you can really get some good nanoparticles. So this the nanoparticles. I don't know. I have not taken the very good nanoparticles we have found of the order of maybe 20 nanometers. This shows again the XRD, and it matches well on in the literature. These are the glucose structures, say, and then they don't change much with because there is no phase transition, so don't change much in this temperature range and with different doses. And this again is a comparison with the commercially available phosphor, and I can see that they are very, very much comparable. But the more important thing over here, you can see over here the dose. Generally, this also we have studied in microcrystalline, so it saturates around maybe 100, 150 gray. But here you can see that this doesn't saturate even up to 10⁵. This is around 10⁵ gray. And therefore, this has applications for measuring such kind of very, very high doses. And these, because in cancer therapy or in your food preservation kind of applications, the very high doses are given. Now, very high doses are given to how the food is preserved. Food is preserved because the bacteria spoils the food. So if you can pack the food and then expose to radiations, so the radiation can kill the bacteria. But if the dose is not proper, then what will happen is with that some radicals will also form and then can make that food toxic. So therefore, it is very, very important to measure those doses also. But there are no phosphors for measuring such. Same thing is in cancer therapy also. You have to plan that because it is associated with a living being or a living person. And therefore, there also for estimating or monitoring these very high doses is very, very important. And these nanoparticles could be used for such applications. Then I have taken this another material, that is LIF-MgCuP. Again, this material we have prepared by the simple co-precipitation method, but one has to take care because here we have taken Li lithium chloride and ammonium fluoride over here. And you know that the fluorine atom ion is very, very reactive, and it reacts if you take the glass as your container or glass beaker as your container for this reaction. So there will be reaction, and then all that impurity will go into your material. So to avoid that, one can use this as a Teflon. So we have used so that there will not be any contamination over here. So whenever you are using such kind of techniques, what one has to see how your technique should not contaminate your material, and so therefore I have chosen these things. So in this material also we have by changing the concentration of the ingredients or the starting materials, and by adjusting the pH of the solution and the amount of ethanol that we have used for this thing, one can also change the morphology, because we also had to see whether the morphology also has some change on the luminescence properties of this material. So here you can see that we could synthesize this long nanorod or needle-shaped this kind of particles. Then by changing some parameters, we could also synthesize or prepare this in cubic or particle form. And also by the same technique, we could prepare this is microcrystalline. And we studied these luminescence characteristics, and you'll see that the glucose structures change by changing the morphology as well as by changing the particle size. So this is for microcrystalline, then this is for nanorods, and this is for nanoparticles. So it changes because maybe there is some crystal field effect, or because in this nano form, whatever little change occurs over there, the properties get enhanced, and these kind of things we could not study in microcrystalline. So therefore, in material, it's not only from application point of view, but for studying some different properties. Even same thing, we had the same experience with or studying these phase change or effect of phase change on these luminescence properties. Then we also have studied some JDNO, and this is by reflux method. So we this flow chart shows that we had taken zinc acetate with this is an impurity chloride, so this is soluble in water. Okay, so we refluxed at 80 degrees for 6 hours, and then reacted with sodium hydroxide in ethanol, and put dropwise, and we found that there is a milkish color changes, and then by centrifugation you can take out, then dry, and you can use this. So by here we found that by changing the temperature of the solution itself, you can change the particle size also. And this shows the XRD of different. And also, if you change this neodymium concentration over here, so there is a little shift in the XRD also because of some stress formed because of the more and more impurity in the material. And therefore, these lattice parameters also change. And then we also have studied this by photoluminescence studies to study defects, and then you can see that by again increasing the concentration, the defects levels also change. We also studied Raman spectroscopy. And from application point of view, you can see that if we expose this material, nanomaterial, to UV light, the surface defects might be getting more created over there, or they change the concept, and therefore this green emission changes with the exposure time. So if you keep the power of your UV same and go on changing the this exposure time, you will see that there is a change in this green band, and by this you also can monitor your UV radiation. And also by thermoluminescence, because of this radiation, some traps also might be getting developed or generated over there, and by then stimulating them by thermal stimulation, you get such kind of glow curves, and you will see that with the radiation time increasing, this also is intensity increases, and that is how you can use it for UV radiation monitoring. And also, as the niobium is magnetic, okay, so this makes this material ferromagnetic kind of this thing. You can see that there will be very tiny these magnets or dipoles magnets will be formed, and then this material could be thus used for some information storage or applications. Another application of this is really a multifunctional kind of material, and this is also known as photocatalytic. But as you go from microcrystalline to nano crystalline size, as earlier I told, that the surface area increases, and this surface here, the application of this are because surface defects over here. Okay, if you have more surface, you will have more photocatalytic activity over here. So in this reactor, this is a rhodamine B dye over here solution, and this is UV light, and this is made up of quartz because glass absorbs this thing. Okay, and therefore we studied with time, and you can see that within 1 hour or so, this the colored this solution becomes colorless, means dye is disintegrated over there. And this has a lot of applications in your cloth industry and all that, because these dyes generally they are used for dyeing the cloths, and whatever is affluent, that is remaining, whatever solution is there, that is just flown into your drains and then goes to rivers, and then you have water pollution kind of this thing problem. Now that could be monitored or solved by using this kind of nanoparticles. Then we wanted to see or do some band gap kind of tailoring over here. Okay, so we have studied over here JDNS, the composite system. And again, we have the same very simple kind of, again, the same technique over here of co-precipitation method. And you can see that in the XRD, okay, so you have this ZNS here, and if you go on annealing this at different temperatures, okay, so this ZNS gets oxidized, and you also get the another phase, that is the ZNO phase over here. But ZNS is in cubic phase, and ZNO is over here hexagonal, and therefore by annealing we have prepared this in rod form. So by annealing there is a stress developed, and because of that the nanorods they break, and you get then in particle size, and also at very high temperature then they get in bigger size. So with annealing temperature, you will see that the lattice parameters also change because of the composite system, that some ZNS gets converted into ZNO. And here also you can say that the percentage of phase, okay, so one phase goes on reducing, another phase percentage of another phase goes on increasing. And here that is what I was talking about. So this is the band gap of ZNO, and this is ZNS, and in this you can really by changing the phase of one into another, you really can engineer the band gap of this material. And this shows that with temperature how the band gap changes. And also when the band gap is changing, the other defects levels or their levels, or the because of the sulfur ions, or because it's not completely stoichiometric over there, that ZNO. So ZNO, even ZNS. So therefore, by changing that, your this green peak or this in ZNS or ZNO, this also shifts. So there is a lot of or a great bigger this blue shift also we found in this. Then the same material or the same technique we have used to synthesize this ZNO, ZNS core shell kind of structure. So what we have done is we have firstly synthesize ZNO by the same technique, and over which again then we also coated or coating of this ZNS. And again, the synthesis is very, very simple that we have discussed earlier. And here, then you can also really form the ZNO core shell structure. And if you just soak this kind of structure into KOH aqueous solution, so this ZNO gets dissolved, and you also can form very beautiful ZNS nanotubes. So for many applications, you will need, because the surface area now increases from outer side and inner side also. So for some kind of gas sensor applications and other sensor applications where you need a more surface area, so these nanotubes could be used. So you can see over here, so this is for ZNS, okay, and this is for the composite dart system, and these are the nanotubes over here. So by tailoring a little bit the same kind of system, you can really find a different kind of or make different kind of. And this also shows, the XRD also shows the same thing. Okay, so this is the ZNO, and then this is a composite system, the core shell kind of thing. And then when you soak and this thing, you get the ZNS, this nanotubes. And also band gap also changes. This also shows that there is some change. Then I will discuss about some another method of the hydrothermal method. Here also, because there are many different kind of phases occur during the heating, and Al2O3 doped with carbon is a very, very sensitive TLD material, as well as this is a optically stimulated luminescence dosimeter also. And therefore, we wanted to see this effect of phase change on these, because this will have again repercussions on its performance as a TLD material. So again, this is done by hydrothermal method. So what is called as autoclave. So we have but we call it as a bomb, because the pressure inside. So with solution, we keep whatever solution inside, and we close it very tightly, and then we heat it at around 250 to 300 degrees centigrade, and you can imagine how much pressure inside could be. So therefore, one has to be really careful about. So then we have found different kind of phases of this thing. By annealing, then the phases will be changed. So the lattice parameters will also be changed. So you have some hexagonal, tetragonal, monoclinic, and cubic, and orthomic, and all sort of phases. And then these are the different kind of phases, and we wanted to see what is its effect on the locus structure and other luminescence properties also we have seen. But specifically for the sake of limited time, I have shown only this thing. So there is a lot of change in its luminescence properties. Then this I have taken from D. Harinath and his group, this example of soul gel method. And they say that they have reported very ultra fine Al2O3 EU2 plus. Again, this is a red phosphor, and they said they also have given the method to prepare some security ink, what they call as, because in currency notes and for their applications, you know that there are some features which are not visible in room light. But if you shine this thing with some UV or some light of higher energy, that you will see the luminescence over there, and that is how those features could be seen. And this is important for some security purpose. This is important in some forensic applications also. So they have prepared this by simple, this again, soul gel method. So they oxides, both impurity and this yttrium oxide, they dissolve in nitric acid and in small amount of, and then again, then form some solution of that. And they say the pH of the solution is very critical in tailoring the size of this particular phosphor, and then they use this citric acid. I think somewhere, yeah, citric acid as a gel. So gel is formed. Then by sintering this gel, you get this kind of nanoparticle. So here you can see that in room light you don't see, but in under UV light you see very intense this kind of color and very intense luminescence. And this slide again shows the nanoparticle size and all that, maybe around 10 nanometer or so they have mentioned. And here you can see that in they have prepared the ink and then written this was done at NPL. So they written NPL. So in room light you will not see this thing, but in this under UV you will see very intense kind of color. Then this particular material Al2O3 was very interesting to us because this is a very, very sensitive kind of TLD material and OSLD material, and this is the only OSLD material phosphor commercially available. So therefore people but it is the synthesis is very, very difficult because doping carbon in this is not possible unless you have that vacuum furnace, and again this melts at very, very high temperature around 3000 degrees. So therefore it is very, very difficult to synthesize. So we wanted to see by thermal plasma method, can we synthesize this material? Also, in this particular material, this method, you will see that bulk or a large amount of material you can prepare at one time. So this again will be a very great advantage. So this is the thermal plasma kind of reactor is there. So this sketch shows sketch and then what is happening inside, and this is the real machine we have used. So what we have done over here, we have taken aluminum and and mix aluminum powder with graphite or doping this carbon, and then this is a plasma over here generated, okay, and then oxygen gas is inlet over here. So these ions, aluminum and carbon, then react with oxygen. So some of the carbon also gets reacted to get the carbon dioxide, but at the same time, if you control the amount of these, so still some carbon remains inside, and you get the aluminum oxide carbon. And this shows the very good nanoparticles over here, and this also shows the particle size distribution. The size is maybe around 30 to 37 nanometer. And then this when we synthesize, that was in some gamma phase, and when you anneal at high temperature, it goes to this alpha phase, and you can see that because of the phase change also there is always this change in the glucose structure. So generally this material is used in alpha phase, so therefore there is no problem. Once you achieve that phase at very high temperature and quench it, so it is a frozen, so not much problem. And also we have seen these are the OSL decay curves, and this dose response, and then you can see that you can measure up to 10⁻⁴ gray over here using this. Then I will. We also have synthesized this magnesium borate doped with the dysprosium. This material is of very great interest to us because this is what is called as a tissue equivalent material. Lithium fluoride and this borate, and there is a barium oxide, and these are the only few materials are there which are so this is a tissue equivalent material, so the energy response is very flat. Also the Z effective is approximately equal to your tissues, the Z effective of carbon and tissues, and therefore the damage caused to your body is a similar damage, you can say, or or the interaction is similar kind, and therefore this could be used in a mixed field of radiation. And in this method, you can see that the very simple method. So you take your material and some oxidizer over there, some fuel kind of thing, and you just burn. So the advantage of this method is you just can synthesize material in 5 to 10 minutes. And again, you can see that in nano material, you can measure even 10⁴ gray on, then the sensitivity and other things are comparable. And also you can see these nanoparticles. We also have studied some defects over here by some other this ESR method. And in my last this thing, now I will talk a little bit on films. So we also have some experience of synthesizing this. We had synthesized, we had taken ZNO is generally N-type. So we had taken P-type silicon substrate and grown these nano rods over that. So to form the heterojunction nanodiodes array. And then this device we have prepared for monitoring UV. So this is the sketch of that RF sputting unit, and this is the actual machine that we have used. And you can see that very uniform these hexagonal nanorods are formed over here. And then this is the device. So this you have P substrate. These are N type of ZNO nanorods, and this is for contact U. We have gold coating over here, and this silver contact we have for again for this contact. And then you shine this with UV and you will find photocurrent. And studies we had. So in reverse bias mode we have used, and you can see that with applying more biasing you get more and more photocurrent. But at the same time, if you have fixed biasing and you change this UV power, and you see that the photocurrent increases. And the properties of this our device we found better than the commercially available. We tested with a couple of other commercially available such kind of monitoring such sensors. And also there is another advantage of this sensor is that this is visible light blind or doesn't show any photocurrent. So therefore there is no interference. So you can use only monitor or ABC or this UV only. And this is the repeatability and other response time and other things we have seen. And the most another important, we have switched on for several days, maybe over a month or so, and you'll see that there is not much change in its output. It's a very, very stable device. Yeah, we could.
You have 2 minutes, so we are running short of time.
Yeah, I'm just concluding. I'm just in 2 minutes. I'm concluding. Could have indicated me maybe 2 minutes more before, so I could have. So then this is also we have synthesized this by CVD method. So this CVD facility we have developed in our laboratory, and this is the setup. And here we have taken silicon substrate. We have coated with gold film over here, a thin film, and at certain temperature, then when it melts, it forms some droplets. So this is very, very important to monitor the temperature. And then these acts, the important of this kind of technique is they act as seeds for these nanorods. And that is how the nanorods are formed. Or you can form these seeds and also grow on those seeds by other technique also. So that is the beauty of. So again, but then you have to monitor thickness of this gold film, and then the reaction duration, and the substrate with substrate also. So, but then this we have found that there is a good current density of this field emission, and then this material or this film can be used as a field for field emission applications. So I will not go into all other things. This is ball milling and all that. So finally, in conclusion, I can say that research in this nanotechnology or nano research, I will say, is not that costly, not that very, very costly, because some of the methods we have seen are very, very cost effective. And one can do in very small laboratories also. The only thing, the hurdle in this kind of research is the characterization part. So one can synthesize these materials in their own lab and then collaborate with other groups where these facilities are available and can do good work. Thank you very much. Any questions?
Thank you very much, sir. Thank you, Professor Sahare, for your work on giving us a nice overview on the synthesis of nanocrystalline crystals and the techniques you use for precipitation, and also the interesting thing about them from a physics point of view, as well as from an application point of view, where they can be used in photocatalysis, degradation of dye, water pollution, security, ink, etc. It is a very nice introduction to the topic and the many avenues open for research in this area. Thank you so much. If we have time just for one question, Ritesh, if anybody has. Ritesh, are you there?
Yes, please.
Yes, is there, are there any questions?
I think Ritesh has lost his connection. Now we have no questions for this talk, I think.
Okay, so let's thank Professor Sahare again. Thank you so much. Now we come to the last talk of the session, and we're very happy to welcome Professor Meng-Lin Tsai from Taiwan. Good afternoon, Professor Tsai.
Good afternoon.
Probably I gather he's the youngest speaker for the day. Professor Tsai is from the Department of Material Science Engineering at the National Taiwan University of Science and Technology in Taiwan. And I've been given a very big biography, but I will condense it so as to not keep you away from Professor Tsai's lecture. So briefly, Dr. Tsai joined the National Taiwan University of Science and Technology, and he's been there since August 2018 as an assistant professor. He's done his BS degree from National Tsinghua University in Hsinchu, Taiwan. He worked as a research assistant and a PhD student in Academia Sinica, and his work was on ultra-high vacuum systems and single-atom chips. And he has done his PhD from the Li Huan Chen professor, under the supervision of Professor Li Huan Chen in National Tsinghua University. And in his PhD, he focused on the development of 2D devices, silicon organic hybrid solar cells, silicon-based water splitting devices, and low-dimensional photodetectors. In the past 5 years, he has published over 30 peer-reviewed papers in SCI journals with over 2,000 citations. And his first author papers were published in high-impact factor journals, including Nanoletters, Advanced Materials, and ACS Nano. He joined AU Optronics and worked as a senior engineer on the liquid crystal display array and cell design platform unit. And after joining his current assignment, his main research interests are low temperature and large-scale 2D materials and synthesis of air-stable inorganic perovskite quantum dots for display applications. There's a long list of his expertise. I'll quickly go through them. WRGB gamma measurement, physical vapor deposition, chemical vapor deposition, SEM, electron beam lithography, photolithography, finite difference time domain simulation, and ultra-high vacuum systems, as we heard before. And he works on many research fields like color washout improvement, washout diffraction film design, VCOM adjustment, 2D materials, and so on. I should not take too much time. It all sounds very fascinating, Professor Tsai, and we really look forward to hearing from you on a functional film for the next generation display technology. Professor Tsai, please.
Okay, thank you very much. Can you hear me? Am I audible?
Yes, we can. Yes.
Okay, thank you very much, Professor Venugopalan, for the nice introduction. Can you see the slides?
Yes, we can
screen?
see. Yes, we can
okay,
see.
Let me use the pointer. It's my honor to be invited to join this webinar. And actually, this is my my first experience, okay, to be online, because as we're still having some normal classes or normal conference here. So I also hope that everything's good and you all can take care of yourself, and I'm gonna also pray for you all, okay, to go through this situation. And today I'm gonna present the topic of functional films for the next generation display technology. And I'm currently working as an assistant professor in the Department of Material Science and Engineering in Taiwan University. And since Professor Venugopalan has also already introduced me, one point I'm gonna emphasize is that before I joined NTUST, I was a senior engineer in the liquid crystal technology department in AU Optronics. Okay, so before I come to join NTUST, I was working in the industry. Okay, so the first part of my topic will be more related to the industry and how we work as a research development engineer in the local company such as the AUO. Okay, AUO is also a famous supplier for companies such as Samsung or Sony. Okay, the two largest LCD or the TV display manufacturing company. Okay, and first of all, I'm gonna briefly introduce where is the NTUST. I guess heard about Taiwan, and just in case that you don't mix the Taiwan with Thailand, we're actually southeastern apart from China, and just besides the Taiwan Strait over here. And you can see NTUST is located in the Taipei City, which is the capital of Taiwan, and this is the tallest building right now here in Taiwan. It's called the Taipei 101, and this is the night view of Taipei City. And below you can see the NTUST campus, and we also have the highest percentage of international students in Taiwan. So, and most of the students come from Southeastern Asia countries. For example, you can see this Indian flags here, and also some students come from the Indonesia or the Vietnam. And we actually have two campuses here, and the one campus located in Taipei City, which is the Taipei main campus, one street across from the National Taiwan University. Okay, so this is actually the National Taiwan University, and this is the NTUST. We also have another campus in Zhubei, okay, which is near Hsinchu. There's a famous science park, and since we work on many industrial collaborative projects, okay, so we have another campus here for doing some industrial related research. And now I'm going to talk about my research for a little bit, and this is during my past PhD experience, I mostly work on devices instead of material analysis. Okay, so even though I graduated from the Department of Material Science, I mostly work on, we collaborated with people growing material or synthesizing material. We come up with some devices for optoelectronics applications, such as device photo detectors or solar cells. Okay, but since I joined AUO and work on the development of liquid crystal display, I started to develop some functional films for the company. Okay, instead of instead of doing some something about liquid crystal, I don't really do the liquid crystal research. Instead, I work on the functional films in order to improve the viewing quality of the liquid crystal display. And based on that, I go a step further and started to become more interested in the quantum dot, because QLED becomes a more popular TV for large scale and high-end TV recently. Okay, so after I joined NTUSD, I began to do some QD related research. And this was also from my past, so I'm going to just briefly introduce. I work on the structural engineering of silicon solar cells, for example, fabricating nanostructures on top of micropyramids in order to improve the light harvesting or the omnidirectionality of the solar cells. Okay, we also mixed 2D quantum dots, such as graphene quantum dots, with the organic solutions such as P.PSS to fabricate these hybrid solar cells with enhanced optical and electrical properties. And since one of my expertise is e-beam lithography, okay, I also try to come up with some nano device, including 1D nanowire photo detectors or the 2D atomic layer, monolayer photo detectors. And also we work on some, we use some carbide or nitride material to come up with some harsh photo detectors. Okay, and this is the outline of my topic today. Okay, I'm gonna share with you two of my topics. One is from my industrial experience, which is called the light diffusing film, improving the viewing angle performance of the liquid crystal display. And the second one will be, which I'm working on right now, which is called high performance perovskite quantum dots, and mix it with cellulose nanocrystal to come up with a hybrid film for improving the stability of these type of quantum dots. Okay, so as you know that there are different type of display. One, depending on its alignment of the liquid crystal, there are two types, including the VA, which is called the vertically aligned display, and the IPS display. Okay, I'm not going to go to detail of this type of liquid crystal orientation, but instead I'm going to tell you that the difference between the viewing qualities between these two types of display. For example, due to the orientation, the VA display provides very good contrast in the normal viewing direction, okay? But for high angle, you can see that if you see this liquid crystal display from a large angle, actually you see the short axis of this liquid crystal, okay? And the long axis and the short axis provides different transmittance, okay, for the cell, okay? So, for example, for this type of liquid crystal, you can see that the transparency for transmittance for the long axis will be lower than the transmittance of this when you viewing at the short axis. Okay, so what's the problem that this type of orientation will become is that when you're looking at in the large angle direction, you will see a severe light leakage problem. Okay, so the contrast ratio will be significantly dropped when you're looking in the large angle direction. Okay, and for the IPS, the leakage problem is actually almost the same for a different angle. Okay, but one of the disadvantages is that its contrast ratio, due to its liquid crystal orientation, it cannot be very high, okay, because the rotation of this the orientation of this liquid crystal will cause light leakage in all the directions, okay? So if you compare VA display with IPS display, you will see IPS has a severe light leakage in the normal direction, okay? If you have a notebook with IPS display, if you turn it totally black, you can still see some backlight coming out because it cannot turn all the way off due to the orientation of the liquid crystal. However, for VA display, due to the orientation, in the normal direction, okay, the leakage can be adjusted to be very, very small, okay? But it cannot prevent the large leakage in the large angle direction, okay? So this will induce what we call the color washout problem. I will show in the next slide. Okay. Let's first begin with this table. Okay. So if we compare these two types of LCD with OLED, you can see that because VA and IPS both use in organic backlight unit, okay, backlight source. Okay, so compare with the OLED because it use organic organic cells, okay, for the light emission. Okay, the lifetime will be longer for the traditional LCD. Okay, and the cost will be okay, because the manufacturing yield for this traditional LCD is higher than the OLED. Okay, but you can see that VA experienced a serious color washout problem. Okay, and IPS and OLED has a better angular viewing quality for all the angle viewing experience. Okay. But for the leakage in the normal direction, IPS is not good because it always experiences some the light leakage due to the orientation of the liquid crystal. So this is why you see if you compare IPS with VA. Okay, you can see that the VA display always shows some light leakage problem in the high angle. Okay, and this light leakage problem will cause the image to be different between what you see in the normal direction and what you see in the large angle direction. Okay, this is what we call the color washout problem in the VA display. And traditionally, what we can do to improve this type of problem is that instead of using a single domain, liquid crystal domain, we can try to come up with multiple domain. Okay, the concept is like this. If you watch the TV from this direction, you can see the short axis. And if you watch it from the other direction, you can see the one you can see the long axis and the other you can see the short axis. Okay, so when you see the short axis, you can see white image. And if you see the long axis, you can see black image. And if you view it in the normal direction, you can see something like a gray image. Okay, so you will see large difference for different viewing angles. Okay, but if you try to design multiple domain, you can see that for this direction you will see half white, half black, and for this direction you will see also half black, half white. And in the normal direction you will see gray image. And since your eyes, because the pixel is so small, okay, and your eyes will automatically average, okay, between these average over these neighboring domains. Okay, so you will see gray image, okay, due to the averaging of your eyes. Okay, so you will see not as large difference for the multiple domain as you see in the single domain LCD. Okay, so this is one way which is very popular for improving the color washout problem for the VA display, and it's also commercially used for in the industry. Okay, but you can imagine that by designing this multiple domain, you will need an additional electrical circuit, so it's additional cost. Okay, and what will the additional circuit do? It will block the light. Okay, so your transmittance of your cell will be largely decreased due to the additional electrical circuit. Okay, so for the next generation LCD, people try to come up with a different type of design. We try to come up with if we can put a film on top of the display in order to improve this problem, we won't need to design this multiple domain design. Okay, and the film design is the concept is like this. Okay, by combining two layers with different refractive index materials, okay, you can design some structures between them. Okay, so if you have two different, if you have a combination of high and low refractive index material, if you make this structure the periodicity to be like less than the wavelength of light, it will cause some diffraction. Okay, so this is what we call the Fourier optics. And the method used to simulate this type of structure is we can we can use the FDTD method using software such as ARSOF or numerical FDTD to simulate what can be done to improve the light diffusing of the washout film. And another way you can design some refraction structure based on the traditional ray optics using ray tracing method and with software such as Light Tools or TracePro to come up with this refraction structures. So what's the difference between them? For diffraction structure, the light enters the washout film following this diffraction equation, E sine theta equals n lambda. So you can see that for different wavelengths of light, if we come up with a specific periodicity with blue, green, and red light, they have different wavelengths. Okay, so you can see that if we have normal light passing through this diffraction structure, you can see that the blue light will be diffracted to like 30 or 31 degree or so, and the red light would be diffracted to 48 degrees. Okay, so this is one concept or method that can be used to design such structures or the films. Okay, and another type of film is called a reflection film. Okay, you can see, for example, here we have PET on top of PMMA, and we design a trapezoid structure. Okay, so whenever the light enters this film, it will come to the trapezoid and the side wall of this trapezoid structure. Okay, and due to the Snell's law, you can see that the light will be refracted to the large angle direction. Okay, and when it comes out again, okay, due to different type of refractive index combination, it will be refracted to a specific angle. Okay, this is what we call the light diffusing properties of the refraction film. Okay, so you can see in this case, actually the blue light will be refracted to like 40 degree, and the red light will be refracted to 35 degree. Okay, so this this color dispersion mechanism for this these two may be different. Okay, why? Because you can see that for this type of mechanism, the blue light actually diffuse to smaller angle, but for this type of structure, the blue light actually diffuse to the larger angle. Okay, and we try to compare these two mechanisms for the design concept. Okay, and in the last slide we talked about the normal angle image light entering the film. Okay, and what if the light enter the film from a larger angle? What we can see is that we need some we need to revise this equation to like something like this. Okay, and if we do some simulation, we can see the blue line here, red line here, and the purple line here shows the light entering from the 0 degree, 10 degree, and 30 degree respectively. Okay, and after entering this diffraction structure, it will be diffracted to certain angle. Okay, for example, for like light in the normal direction, it will be diffracted to like 30 degree or minus 30 degree. Okay, so you can see that for larger angle, you can see that it will be diffracted to the smaller angle. Okay, and for the refractive structure, you can see that for smaller angle, it will be refracted to larger angle, but for 60 degree light, you will see that due to what we call selective light diffusion phenomena. What is the selective light diffusion phenomena? Is that you can see for this type of structure, in order for large angle light to refract it back to the smaller angle, you need to encounter this total internal reflection. Okay, if you encounter this side, it will be diffused to a larger angle. So only if you encounter this sidewall here with total internal reflection, it will be reflected back to the smaller angle. Okay, so you can see that the diffusion of peak at large angle will be larger than the peak at the smaller angle. Okay, this is what we call the selective light diffusion. So, so which way is better? Okay, actually for the designing, we actually have some target. Okay, for example, don't sacrifice too much contrast ratio in the normal direction. We don't want to sacrifice too much transmittance loss in the normal direction. Okay, so we simply simulate this type of structure. Okay, for and we have a commercial TV with no diffraction film as the reference. Okay, you can see that normally in the normal direction, the contrast ratio is like over 33,000, which is good. But the contrast ratio at large angle will be dropped significantly. Okay, so our goal is to increase the contrast ratio, okay, at the larger angle. Okay, you will always sacrifice. Okay, there's no way you can improve the large angle without any sacrificing the smaller angle. Okay, so what we can do is we can adjust. Okay, for example, we want in the normal direction the contrast ratio to be above like 2005. We to improve the contrast ratio at the 60-degree large angle viewing direction to like over 300. Okay, so based on these designing target or condition, okay, we can try to compare with diffusion films with different structures. Okay, you can see that by comparing the refraction structure with diffraction structure, the sacrifice in the normal direction is less for the refraction structure. Okay, so this one is more ideal for designing the diffusing films for the VA display based on our requirement. Okay, so you can see the diffraction because there's no selective light diffusion. So the contrast ratio dropped too much in the normal direction. Okay, and in the large angle direction, the contrast ratio enhancement is not as good as the reflection film. Okay, so and we go a step further to like we have a design target to maintain the transmittance drop below 10% and the contrast ratio drop below 25%. Okay, we try to analyze what will cause the transmittance to drop. For example, this part will induce the transmittance drop because light coming in this direction will be diffused to large angle direction. Okay, so we can design based on the ratio of this part with the period of our structure. Okay, we can control the transmittance drop. Okay, so we come up with our optimized structure. Okay, by designing a structure with a height 20 micrometer with like the taper angle, which is the angle of the sidewall of the trapezoid, to be like 86 degree. 86 degree is this theta angle. Okay, and with a different width combination for the trapezoid structure, and the pitch is the period of this structure. And of course, we come up with we need to contact the supplier for the film fabrication to come up with this refractive index combination. They have different film material with different refractive index, and they have different epoxy with different refractive index. Okay, so we come up with this combination. You can see that by using this type of structure, we can improve, okay, the contrast ratio in the large angle direction. And because your eyes will be more sensitive, okay, for like contrast ratio below 1000. Okay, so the contrast ratio enhancement from like 150 to 300 will be very significant, okay, for your eyes. And then the contrast ratio in the normal direction only drops like about from 3,300 to like 2,800. So it's still okay for our application. So this is based on the simulation. Okay, so this is based on the experiment. Okay, we actually contact our supplier to come up with based on our simulation to come up with the film, and then we put the film on top of our display, and you can see that the transmittance. We have two different designs. Okay, you can see that the transmittance dropped by like 3 to 4%, and the contrast ratio enhancement at large angle can be improved from 100 to 200, over 200. Okay, for the actual film. Okay, and compare with our competitors, we have a better improvement at the large angles for better viewing quality. Okay. So by proper design, we can achieve high transmittance diffusing films with excellent high angle picture quality. Okay, and of course there are some side effects. For example, this structure, trapezoid structure, will cause some image blur problem. Okay, due to the total internal reflection of the light. Okay, so and also as I said before, because we use different combination for the refractive index. Okay, there will also be some color dispersion problem here. So if you look at a large angle in your display, you will see some rainbow image on your display. Okay, so this can be further improved. Okay, and I think my past previous colleagues are still working on it. Okay, so for example, multiple taper angle, you design some structure with a more smooth angle or multiple angle or concave structure has been designed to solve this issue. Okay, so this is about my first topic, and I will go quickly through my second topic, and this is still an ongoing project. Okay, so we try to come up with some quantum dot enhancement films. Okay, and the quantum dots are like one zero-dimensional material and with light emission properties. Okay, and it can be used for display. For example, if you compare with this OLED TV, you can see that quantum dot, due to its properties such as narrow emission wavelengths. Okay, and or the light emission for the quantum dot is very pure, okay, compared with a traditional phosphor, okay. And what I mean by pure is like the emission width is narrow, okay. So you can come up with a larger triangular shape for the RGB area in your color gamut diagram, CIE diagram, okay. So if you compare the QLED with OLED, you can see that the QLED exhibits even better color performance than the traditional OLED display. And also, OLED suffer from the instability. Okay, the axis here is the time, and you can see that for OLED TV, the color will change with time. So for the improved color performance, you can see that QLED TV actually has some show the better picture quality than the QLED TV under the same brightness. And the traditionally used quantum dots are cadmium selenide and indium phosphide. Okay, and the indium phosphide are still commercially used for most of the QLED TV. Okay, but cadmium selenide is restricted for future application due to the toxic cadmium material. Okay, so it cannot compliant. It will be restricted by the rules. Okay, restriction, and for the electronic devices sold in European, for example, European Union, you need to comply with the rules, the compliance. Okay, and but commercially used indium phosphide still have some problem. For example, is quantum yield is not as good. It's less than 60%. Okay, and its emission width is not as narrow as the cadmium selenide. Okay, and also because indium is a rare earth material. Okay, so this indium phosphide is more expensive than previously used material. So people try to come up with new type of quantum dots. And one popular material which is widely studied recently is called the perovskite quantum dot, cesium lead halide material. And you can see that the quantum yield is good and the emission width is good, okay, for this material, okay? And even though it has lead, but the rules restriction for the lead is not as strict as cadmium, okay? So the lead can still be used for electronic devices, okay? But the most important problem for this type of material is that it's unstable, okay? It's quite unstable. And this slide just shows the properties of perovskite quantum dot. And this is the synthesis procedure, okay? The most popular procedure, one is called ligand-assisted reprecipitation. Is first you dissolve the precursor into the solvent, and then you mix them together and stir them on top of the hot plate, and then you try to put it into the anti-solvent, okay? And you mix the precursor with the capping ligand, okay? So when you inject in the anti-solvent, the quantum dot will automatically be formed in the anti-solvent, okay? And the other widely used procedure is the high injection method, okay? And this method is also widely used for traditional quantum dots such as cadmium selenide or indium phosphide. Okay. But I'm not gonna go into detail of these two procedures. Just give you a few view of the different procedures that can be used to synthesize the perovskite quantum dot. And also the microfluidic reaction has also been devised in order to precisely control the emission wavelength of the perovskite quantum dot. And also there are other methods such as template method. You can use mesoporous silicon dioxide with a specific pore size, okay? And then you soak it into your precursor, and then if you remove it, and the quantum dot will automatically form inside these pores. And as I said, the most important problem for this perovskite quantum dot is the stability problem. Okay, it can be classified into crystal stability, and interface instability, and the environmental instability. Okay, and these are the strategies to improve the stability. Okay, so for example, the crystal structure instability can be used by doping different different materials. And for the environmental stability, most of the environmental stability can be solved by using encapsulation method. Okay, but there's one problem remains, is the light-induced crystal regrowth problem. Okay, so what is the light-induced crystal regrowth problem? As you can see, we for the quantum dots, we traditionally use capping ligands such as oleic acid or oleamine for capping and preventing the quantum dot to grow bigger. Okay. However, the traditional capping ligands the interaction between the traditional capping ligand with the quantum dot is not very strong. Okay, actually it undergoes a dynamic exchange between ground state and the free state. Okay, so if you have light excitation, okay, some of the ligand will be peeled off, and if you have neighboring quantum dots with capping ligands peeled off, you will aggregate into larger crystals, and the light emission properties will be disappear. Okay. So in our lab, we try to synthesize some perovskite quantum dot material. For example, this is blue, green, and red emission quantum dots, and we try to characterize its size. And we collaborate with some people with some groups with inkjet printing of nanomaterials. So this is inkjet printable, and we can also come up with the quantum dot powders. Okay, but the most recent project I want to share with you in the next few minutes is the quantum perovskite quantum dot with cellulose nanocrystals hybrid films. Okay, we actually use sulfate functionalized cellulose nanocrystal, and unlike traditional capping ligand, okay, we mix the CNC position dispersed solution with our quantum dot precursor, and we stir it at the room temperature. Okay, and then we pour it into the vacuum filtration device. Okay, so we can come up with we can come up directly with the film. Okay, after this vacuum filtration process, and we put it in the oven like for 50 to 60 degrees, and it will be directly dried. Okay, and upon the dry until it is dried, you can see the perovskite quantum dot, and under UV light you can see this green emission coming out from the hybrid film. Okay, so what's different between this and the traditionally used capping ligand? It should be noted that for this type of procedure, we did not add any traditional capping ligand such as OA or OLA. And without the quantum dot, you can see the CNC film is actually highly transparent over, it's actually over 80% transmittance in the visible light region. So the underlying mechanism is that the sulfate functional group can be used to replace this missing halide defects in the perovskite quantum dots. Okay, and actually the size of this, actually this is a long chain structure for the CNC. Okay, so unlike traditional ligands, okay, the quantum dots inside the CNC looks like this. Okay, you can see that unlike traditional ligands, which quantum dots are situated side by side, the perovskite quantum dots inside the CNC, actually they have spacing due to the long chain of CNC, long chain properties of the CNC between them. Okay, so you can see it's more unlikely for them to undergo something like 2D aggregation inside this hybrid film. Okay, this CNC, because they are not to a side by side. Okay, but one possible problem that may cause is that upon the formation of quantum dot, it is already too large. Okay, so it is crucial to control the ratio of CNC and the PQD precursors to prevent forming these too large crystals with not as good light emission behavior. So we come up with different light emission wavelengths. We come up with these hybrid films with different light emission wavelengths from 449 nanometer all the way to 600 48 nanometer. And actually, the red CNC film is still ongoing study, because it is other than the photo-induced aggregation problem, it exhibits some phase transition problem. Okay, so this part is still ongoing in our lab. Okay, so for this hybrid film, we evaluate this green emission CCM-led bromide IPQD hybrid film, and we compare with the traditional IPQD film and spin coated on the glass substrate. You can see that under a continuous UV condition and under high temperature condition and under ambient condition, it all exhibits superior stability compared with the traditional IPQD. Okay, so this is a brief.
Wind up. We're running a little short of time. Can you wind up in 2 minutes?
Okay, this is already the summary. Okay, so just give me 1 minute. Okay, and I'm gonna quickly summarize. And first, the functional films with refractive index can be designed to improve the picture quality, and our goal is to prevent sacrificing too much viewing quality in the normal direction. Okay, we want to improve the large angle direction, but we don't want to sacrifice too much normal direction. And quantum dots have been widely adopted in the LCD. And what we do here is we try to combine sky quantum dot with the CNC to come up with a hybrid film with significantly improved stability. Okay, and enabling the development for practical application. Okay, and thank you for your attention. Thank you all.
Thank you very much, Professor Tsai. That was a very interesting and exciting talk, and your work seems very incredible, improving LCD display by engineering structures and materials using techniques and software. There is just, for many of us, display techniques for just going from conventional to LED to LCD to OLED, but you showed us that there's so much more that can be done. And though the physics is very simple, I can imagine how much the technology involves and the research and the optimization of various parameters and the work on quantum dots is especially very interesting as for the future high definition displays. So we really look forward to more things from your lab, and wish you all the best. And thank you so much for joining us today.
Thank you very much.
With that, we come to an end of both this conference and the session. So let me thank all the speakers again, Professor Lerch, Professor Khanna, Professor Sahare, and Professor Tsai. Thank you very much for being with us. It was wonderful. We got to hear a wide range of topics and got to know of your incredible research. I've been asked by my department to also kind of tell you something about ourselves. So for all the people who are listening in, this is the University School of Basic and Applied Sciences, and we are part of the Guru Gobind Singh Indraprastha University, which is a state university of Delhi. And this is one of the oldest schools. And our university is largely engineering oriented and management and professional courses oriented. So as a science school, we've tried very hard to fit in, and I think we've been doing pretty well. In the initial years, of course, we were teaching our physics first year courses to all the engineering schools, and then slowly we evolved our own program. So currently we have two programs of our own, which are Masters in Technology in Engineering Physics and Nanoscience and Technology. And for all our audience that is listening, especially from India, we encourage you to encourage your undergrads to apply for these programs. And we also have a vibrant research group. They are a small faculty, around 10 in physics, about 6, maybe 8, sorry if I'm wrong, in chemistry and 3 in math. And we all work in diverse areas, and I can sort of say that a common thread is material science, exploring it whether from the nano angle or doing solar photovoltaics or many other things. So I encourage everybody to visit our website and to check out our faculty. And please tell your students to also apply for our programs. They're good, and I believe after seeing all these talks that there's a future in studying these subjects. So thank you very much, and I'll hand over to Chitra to the next step of this program.
Thank you so much, Professor Anu. Thanks a lot for the session chair and also for giving us a clear picture of the USBAS and its programs. It was a very engrossing, enriching, thorough and informative session indeed. I thank all the speakers for enlightening us with their valuable views. I'm sure the participants have benefited highly by today's talks. I now request Dr. Yogesh Tyagi, co-convener of the symposium, to please give his vote of thanks.
Thank you, Dr. Sipra. Thank you, Dr. Sipra. Am I audible?
Yes.
I take this opportunity to propose a vote of thanks on this occasion. Good afternoon to one and all who are connected with us digitally. I, on behalf of University School of Basic and Applied Sciences, Guru Gobind Singh University, and on my personal behalf, express a sincere thanks to all the legendary speakers of their field of making mind-blowing, valuable presentations. Among the eminent speakers, we had inaugural speakers, Professor Arnaz C. Pandey, Director, IUAC, New Delhi, and Professor Dinesh Kumar, Vice Chancellor, J.C. Bose University of Science and Technology, YMCA, Faridabad. We also had Professor R.S. Katyar from University of Puerto Rico, USA, as a keynote speaker, including the speakers of the day, namely Dr. Meng-Lin Tsai from University of Science and Technology, Taipei, Taiwan, Professor Atul Khanna from Guru Nanak Dev University, Amritsar, Punjab, Professor Lerch from University of Wollongong, Australia, and Professor P.D. Sahare from University of Delhi. We also had six more invited speakers from different parts of the world. They all broadly cover the theme of the symposium, synthesis and characterization of smart materials and their potential application, and enlighten us with their current view. Our chairperson of the session already highlighted their points, and I'm sure that these valuable presentations definitely will be value addition to the research community as well as to the society. Thank you very much to all of you. A big thank you to our Honorable Vice Chancellor, Padam Shri Professor Dr. Mahesh Verma, for his motivation and encouragement toward this symposium. Sir, you are always a source of inspiration for us. I may like to express our sincere thanks to Dean USBAS, Professor Shruti Aggarwal, for our encouragement and boosting attitude. Thank you very much, ma'am, for your kind support at each and every step of the event. I must mention our deep sense of appreciation to our chairpersons, Professor Vaisali Singh, Professor Anindra Datta, and Professor Venugopalan, for chairing the scientific session and obliged us. Thank you very much, sir and ma'am. I also thank to Professor Avnash C. Sharma, Director Research and Consultancy, for his kind help and useful suggestions. I also wish to express my gratitude to organizing committee of the symposium for their valuable inputs. Especially, I want to mention the name of Dr. Ramchandra Gupta, Dr. S. Nileshwar, Dr. I'll be failing in my duties if I won't name my associates for the symposium, Dr. Rajesh Kumar, Dr. Sipra Mittal, and Dr. Anjana Babla. In fact, they were the real heroes behind this also. Without them, this symposium was not even can't be dreamed. I'm also thankful to the participants for making this symposium live. It will be injustice if I won't name my dear students for their continuous hard work. Here, I would like to mention contribution of Amar, Nikita, Yugam, Vishnu, Deepika, Ritesh, and Mukesh. They really helped in shaping the function. Before leaving this platform, I once again thank you to my dear friends, Dr. Rajesh Kumar, for conducting this symposium at a mega scale, and Dr. Sipra for presenting this symposium beautifully. Once again, thank you very much to all of you. Namaskar. Over to Dr. Sipra.
Thank you very much.
Thank you so much, Dr. Yogesh. Today's session and this symposium is now coming to its end. I thank you all for your gracious presence. It was great pleasure in hosting this symposium for you all. We look forward to many more occasions like this. Till then, stay safe, stay healthy. Jai Hind.